Okay. Perfect. Thank you. Okay. So good morning, everybody. I am Michele Sgamma. Today I'm presenting you a work that is actually a work of thesis of Francesco Fontana, which graduated just a couple of days ago, so it's not here. And yeah, it's a work that it's the first step basically in a wider work which follows the spread of electronics and printed circuit boards used into a lot of areas of industries like automotive, which is the closest to our works, but also aerospace, tractor industry, and more. And what we want to do is to deepen our knowledge about fatigue durability, or what is mechanical vibrations, what mechanical vibrations does to printed circuit boards and electronics, in order to, let's say, act on the take, make, and waste life cycle of PCB, trying to avoid wasting PCBs, which are wasted even just one component is broken, or trying to test new materials in order to have more recycling and more circular life cycle. So talking of failures due to mechanical vibration, we can have four kinds of failures, but the two kind of failures we want to focus on are these two, which are solder failure and lead failure. And you can see from the picture below that they are both correlated to the acceleration or deformations due to the circuit board, so the PCB. For this reason, the aim of this work, that is the step zero, is to investigate how is the static and dynamic behavior of the PCB, and to try to model it with different kind of models and to assess which model is the most suitable to describe the dynamic behavior of the PCB. We've done it by comparing, of course, numerical results with experimental results. Here are the models we compared. Three of them, the one you see on your right, are ANSYS Sherlock based, which is a software recently bought from ANSYS. And the first model, the Sherlock model, is fully used on the Sherlock. So just you pick the model from the ECAD and perform the simulation, while the other two, reinforcement and complete, also use ANSYS Mechanical and are of course more complete and more complex. The first two models, the ones on the left, are developed by Francesco, and they can be used with every FEM software, and simply they model different way the layers of the PCB. The first one calculates an equivalent thickness of the copper layers, while the second one include all materials in the calculation, and for every layer compute an equivalent density from the percentage of each material included in that layer. So as for the quasi-static tests, we made this kind of isostatic bending test, which is very different from a 3-point bending. It's more 4-point bending. And we choose this configuration because it's isostatic, and it helps a lot with simulation, with numerical computation of the model. So it makes it a lot easier. And coming to the results, here you can see, you can see even the video of the simulation is quite fast with no problem. Okay, that's a video, but trust me, the simulation was quite fast and easy. And the important part of these results is that you can see the Sherlock column, the Sherlock model doesn't give results for quasi-static testing because it doesn't allow to make them, just dynamic tests, dynamic simulation. As for the dynamic tests, we use, of course, a vibrating shaker, and we acquired the response the vibrating response with fiber optic laser in different points of the board of the PCB in order to see better every mode from 0 to 1.5 kilohertz. You can see here the first three modes, and here are the results of these three modes, which show that for the first mode, which is the most important one, both on FRF that for participation, all the models are quite good in coming to good results comparing to the experimental one. But the first two models, which are the most simple, are even better than the last two, which are far more complex. For the second and third mode, the things are quite different. So the error is a bit larger, but still there is not so much difference between the simplest mode and the more complex one. Even the most complete, the most complex is the worst. This is important if we have a fast look also at the computational effort of each model. The last two models, especially the complete one, require a lot more of computational effort, a lot more of simulation time. And this request is not justified by the accuracy of the results. So for sure, the three models that we want to go farther with the study are the first three one. The first two that are easier, and we can say we can use, we know how they are made. We can use whichever software, so they have basically no problems in the use of them. The Sherlock, let's say the first Sherlock model, base Sherlock one, is precise and also fast. So it's for sure interesting to investigate further, to use with dynamical testing, while the most complex one will be, I think, abandoned for the future works. What will we do next? Of course, we are going to mount components on the PCB and try to investigate, firstly, the dynamic behavior, how this change with components mounted on, and then coming to the fatigue test to perform which are the failures we have seen before. So solder failure, lead failure, and trying to detect them by voltage drop or visual inspection, or even differences in natural frequencies and so on. So I've tried to be as fast as possible. I concluded. I don't know, maybe there are no time, I don't know. Okay, so thank you. This one? No, nothing. This is a this one. This one? Yeah. Yes. This one. This one. Where is it? Okay.
Thank you. I'm Yoshikazu Nakai from Kobe University, Japan. Today I'd like to talk about the deformation mechanism of harmonic structural materials. So this figure shows the schematic illustration of SN relationship for conventional materials. You can, as you know, conventional alloys, the grain refinement brings high strength, but it leads to decrease in ductility. So we have to improve both strength and ductility by designing microstructural design. To accomplish this concept, a harmonic structural material has been proposed. A harmonic structural material consists of the coarse grain structure, and this one, surrounded by three-dimensional network of fine grain structure like this. And this harmonic structure material can be fabricated using powder metallurgy. This is a conventional metallurgy. So to clarify the deformation mechanism of harmonic structural materials, we evaluate the dislocation density in shear and core structures in harmonic structural material by using restoration measurement by diffraction tomography and using ultraviolet radiation X-rays, and stainless steel with a bioharmonic structure as employed. This figure shows the principle of diffraction contrast tomography, originally proposed by French group. If you by tomography, you have to rotate sample. So during the rotation of the samples, you have a diffraction spot for grains that satisfies Bragg diffraction condition. At the same time, you also can see this dark extinction spot like this. So during the rotation, you have more than 10 diffraction spots for each grain, and for conventional material, mass grain materials, you have a lot of diffraction spots. So you have to classify spots into groups belonging to each grain, and then you can construct the shape and the location of each grain by the diffraction spots. So this is an example of diffraction spot like this. You can see a lot of diffraction spot, and they consist of the bi-ring or something like this. And if you enlarge one spot like this, so a spot of each rotation angle belongs only part of a grain, and because the diffraction spot is not completely flat because of the existence of dislocation. So diffraction spots appeared over a range of successive images like this. So we have to conduct summation of contribution belongs to a same grain is required for reconstruction of grain shape. This is a conventional diffraction contrast tomography proposed by French group, and our new idea is use rotation angle spread. This gives information of dislocation density in diffraction plane. So if you measure the diffraction angle spread for each spot, you can evaluate misorientation of each grain by this equation by using by measuring these angles. So you can evaluate the excess dissolution density by this equation. B is Burgers pressure and D is the grain size, beta is the total methylation. D is excess dissolution, not total methylation density, it's the excess dislocation density. So this is a microstructure observed by EBSD. This is a standard harmonic structure materials. So by diffraction contrast tomography, grains smaller than 10 micron cannot be reconstructed. So in this case, we reconstruct grains only in core structure. So we fabricate a special harmonic structure material. In this case, grains in core structure and cell size is large enough to reconstruct by diffraction contrast tomography. This is an example of the grain shape and grain position of obtained by diffraction contrast tomography. This is the homogeneous material. This is a harmonic structure material like this. So you can see evaluate the shape of three-dimensional shape of grain and total methylation of each grain like this. This is a result of measurement of change of excess density in tensile test. This blue marks indicate the homogeneous material, and red marks is the excess dislocation density in core structure of harmonic structural material. So you can see excess dislocation density is homogeneous material is higher than that of harmonic core in harmonic structure material. So it means that deformation is localized in fine grain structure in harmonic structure material. This is the same kind of graph by a special fabricated harmonic structure material. So blue mark shows that excess dissolution density in shell, and red mark shows the excess dissolution density in core structure. It also shows that excess dissolution density is higher than that in core structure. It also indicates that deformation is concentrated in shell structure. So this is a conclusion. So diffraction contrast tomography was successfully conducted by at Springate in Japan. This is a ultra-bright synchronization radiation facility, and excess dissolution density could be measured. In tensile test, the excess dissolution density was increased with increased applied stress. And in tensile test, the excess dislocation density of both structure and harmonic structure was lower than that of conventional material and homogeneous material. In tensile test of harmonic structure alloy, the excess dislocation density of shell structure is higher than that of core structure. Thank you for your attention.
It's a difficult Greek name, I know.
Yes. It's not very heavy. So good morning to all of you. I apologize for the technical difficulties. The topic of this study, which is a research in progress in collaboration with the University of West Attica, the National Technical University of Athens, and the Acropolis Restoration Service, is to detect quantities that could be characterized as pre-failure indicators. So, how could I proceed the presentation? Murphy's Law. I apologize. Okay. So as I mentioned, the motive of this work is to explore and understand the mechanics which are activated when very brittle materials like marble, which are used, for example, in the restoration of ancient monuments, are approaching the exhausting of their loading capacity. So we would like to prevent signs, indicators that could warn in time about upcoming fracture. The final target is to consider comparatively various techniques that provide such indicators in order to somehow obtain quantitative rather than qualitative results. So nowadays, the most mature and broadly used technique in structural health monitoring is obviously the acoustic emission technique. Of course, during the last years, additional ones are used, like, for example, optical fibers or electrical resistant changes of embedded carbon nanotubes elements or GPS systems. And very recently, during the last 10 years, advantage is taken of the experimental observation that while such materials like marble are loaded very close to the exhausting of their carrying capacity, we have electrical emissions in the form of pressure stimulated currents. So in this direction, we attempt to compare all these results and draw new indicators. The experimental protocol is very simple. Very large marble plates are loaded in direct tension. The plates are notched, symmetrically notched, in order to avoid additional difficulties, because you know that marble is non-isotropic and non-homogeneous material. So we have a set of acoustic sensors and a set of electric sensors on the other side of the specimen. From the mechanical point of view, the result is more or less expected. For example, we noted that very close to the notch of the crown, the system abandons linearity very early. while at the central portion of the specimen, we have linear behavior. This is due to the fact that around the notch, we have the generation of the so-called process zone, where the material behaves completely differently. What was not very expected is that the length of the notches tested in this study did not play a crucial role. In fact, it was the presence of the crack rather than of the notch, rather than its length, that played the role of decreasing the load carrying capacity. Now, the next point that it is interesting is that the acoustic activity appears intensive only at the very last loading stages. For the major portion of any loading procedure, the system is silent, I would say, concerning the acoustic activity. And only during the very last seconds, we have strong intense activity. That is why we prefer to plot all the results in an inverse time arrow, the so-called time to failure arrow. This is the second scheme. And plotting this time to failure parameter, we obtain very sensitive analysis for the very last stages of the loading procedure. Focusing our attention on these last loading steps, we concluded, among others, that the acoustic activity, either expressed as the cumulative counts or the energy or whatever, obeys a linear law. You can see here that during the last stages, while the load, the black line, increases and tends to be stabilized for the last 100 seconds, the acoustic activity is described excellently by a power law for both the notches of the notch specimen. And it is very interesting that this law starts governing the behavior of the material of the specimen early from which fracture started finally. Now, if we have a grid of cells, 1 or 2, it is possible to locate the source of the acoustic. And moreover, if we have the source, if we have the coordinates, then we can calculate the distance between successive acoustic events, the Euclidean distance for each group of events. We split the total number of events into the number depending of the overall number of events recorded, and so we have some values of the average distance between the source of the impact between the source of micrograph. You can see here some plots which were systematically. You can see, for example, that at the very early loading steps, the distance is relatively at about 8 centimeters. Gradually, as we approach the last 10 seconds of the experiment, you can see that the distance between the sources decreases and finally stabilizes for the last, let us say, 30, 20 seconds. And then it increases again. We'll see that this behavior. You can see here another. Again, the same conclusions. We have sources, which is gradually decreased and then is stabilized. Of course, if we have more events recorded, then we have more. And the analysis is more sensitive. You can see here an experiment with about 100 events. Then we divided the events into 8 groups. Again, it's similar. The distance between the sources is large, gradually decreases, is tend to be stabilized and decreases again. If we consider comparatively sources, you can see here that initially the source, the average source, is somewhere far from the notches. Gradually it approaches the notch from which finally, and then it moves away. If we have second notch. The same is observed also here. The center of the activity is far away, somewhere in the specimen, and then it approaches gradually the notch. In this experiment, this notch didn't fracture, in fact, due to the asymmetry of the layered material. The fracture started from here and it was propagating in this direction, far from this notch. Similar conclusions are drawn for all the specimens we tested in this protocol. And then we attempted to compare these conclusions with other quantities. Am I out of time? Okay, no. we attempted to compare our conclusions with the F function, which is something like average frequency of hits, or to the power function, the energy content per time of the acoustic activity. And you can see here a comparative consideration of the F function, the P function, and the distance. Indeed, along the major portion of the test, the specimen is silent, and then between 10 and 1 seconds before fracture, while the load is almost stable, you can see here we have stabilization, and we have a mark, which is a very brittle material. And when activity starts, the distance between the sources is stable. It is very small and stable. Then, when it starts increasing again, fracture has already propagated. And finally, we compared our conclusions with the electric activity. We measured the electrical current produced. You can see here again that the specimen is silent concerning both the acoustic and the electric activity, and only at the very large steps, end steps, we have an abrupt increase. You see here the acoustic activity in terms of their function and the electrical activity in terms of the pressure. You can see that the behavior is completely similar, but there is a small difference. The power law that governs the electric activity is activated quite earlier. For example, in this test, the power law started governing the behavior of the node started about 20 seconds before fracture, while the acoustic activity offered the signal about 8 or 7 seconds before fracture. So concluding, there is a variety of quantities that could provide three-phase indicators. You can see them here. But the main challenge is to comparatively in order to obtain more sensitive analysis and as possible earlier about the failure. We believe that the combination could be very valuable, especially for the monuments made of marble. So thank you very much for the attention. Yes. Okay. Yes. It works. Okay. Nice. Okay. Great. I'll start. Hello, everyone. I'm Rachid Ben Sada from the Dupuy de l'Homme Research Institute at Enns-la-Bretagne in Brest, in west of France. It's my pleasure to be here and to have the opportunity to present the work entitled Interlaminar Strength Characterization of Tansilon under Multimodal Loads. This project is funded by the French Agents for Innovation in Defense. The field of ballistic protection is subject to significant challenge. The main of them is to decrease the weight of ballistic protection devices while keeping their properties. These reasons and the others make this field in constant evolution, notably by replacing the conventional materials as metal and ceramics by composite materials, fully or partly, for some obvious reasons that could be deduced from the HB diagram.
The UHMWP composites are known as sacrificial coatings. The tungsten, the material of interest, belong to this family. So, despite the efficiency of these materials, improvements are still possible by hybridization or by multi-material assembly. The main goal of our project is to add a coating layer of lamina for tensilon, but to assess the gain obtained by coating, we have to determine the out-of-plane properties of tensilon. To do this, we have many methods as conventional tests, DCB, ENF, and MMB. Unfortunately, these tests are not suitable for our case because they require crack initiation. We have also SCAF and test testings. The problem of these tests is that they present some edge effects and complex triaxial stress in high stress gradient zone. To overcome these limitations, we decided to use the modified Archon device in order to obtain a uniform distribution of stress and to test the material following a wide range of stress states. So here we give the content of the presentation. We just see the context, and now we'll introduce the material of interest, the tensilon. Here we give a typical UHMWP composite manufacturing process. It's a three-step process that could permit us to obtain the final product. Within the market, we can find four main products. So we will study the tensilon manufactured and provided by DuPont in form of 500 square millimeters plates. And from these plates, we cut specimen with this geometry, as we can see from the pictures. This geometry is in accordance with the Archon testing. This material is provided with two stackings, 0, 19, and plus or minus 45. Here we give some results concerning the material characterization. In the project, we perform material characterization following three velocities, but here we focus only on the weakest one, given that the Archon testing is done with respect of quasi-static conditions. We can see for the two stackings a good repeatability of experimental testing, given the strong inhomogeneity of tensilon. These tests are used to identify numerical model, the Ashin damage model for composites. We can see a good repeatability of experimental tests by the finite element model. Here we present briefly the Archon device. It consists of two half-moon shaped pieces made of high stiffness steel. The holes disposed within the device make it possible to evaluate the material following different stress states. Here we can see at 0 degree, we can test the material following a pure tensile state, and at 90 degree, we can test it at pure shear, and we have also intermediate rate by modifying the angle of testing. The other particularity of Archon testing is the introduction of peaks within the substrate in order to avoid stress singularities and to obtain a quasi-constant stress state. Concerning the adhesive used in the present study, we used the Thermabond TA4610. It's an acrylic adhesive. It's known to bond surface with weak energy surface. And the other advantage of this adhesive is its current temperature. It's about 23 degrees. It's in accordance with the thermal properties, the poor thermal properties of tensilon. Also, the bonding requires some surface treatments. Here we perform also a corner treatment on the surface substrate and the the tansilon surface also in order to increase its energy surface by charging it positively. Concerning the post-treatment of the test, we use digital image correlation thanks to the Aramis technology. The procedure also requires a speckled pattern applied on one side of the substrates. It's the side in the front of the camera. Here we will expose the substrate choice. We did it thanks to the pull-off test in accordance with the ASTM standard C633. And this test permits us to choose the ABS as a substrate for our study, because it's the only substrate that gives us cohesive fracture in all the case when we see that aluminum and steel could give us adhesive fracture, and these results could not permit us to evaluate the out-of-plane properties of tansilon. Here we give a result of the testing of the adhesive alone. The adhesive is used to bond the two substrates of argon at 0 degree, and we can see that the behavior or the response of the adhesive is quasi-brittle. So this behavior could be described by a bilinear cohesive zone model, and we can see that the experimental curve is well reproduced by the numerical simulation using a cohesive zone model. Here we give some results concerning the argon tests following different stress states. And in terms of ultimate loading, there is we obtained a good reproducibility, but in terms of displacement, it's very difficult given that the material is strongly inhomogeneous. And for the 90 degree, there are other tests, but we were able to record only one. But thanks to the cell load of the machine, we were able to obtain the maximum loading of the other tests. So here we expose the envelope of the tansilon obtained by post-treating the argon tests. This envelope could give us the threshold in terms of stress for the tansilon in its outplane direction. Here we give some conclusion concerning this study. So the tansilon is mechanically tested, characterized, and numeric validation is proposed for the weakest rate at 1 millimeter per minute. The ABS is selected as substrate and permabond acrylic as an adhesive. This combination is found the best one to achieve the out-of-plane characterization. And the adhesive behavior is successfully validated numerically by cohesive zone model. And finally, out-of-plane properties of tansilon are successfully characterized through the modified argon test. Here we give some outlooks for this study. Numerical validation, we propose it by including the composite. For the moment, we just validate the behavior of the adhesive. And also a comparison will be done between quasi-static and the main idea of the project to test the assembly following very high strain testings. Thank you for attention.
Okay, perfect. Thank you. Well, thank you for the introduction. Today, I will speak about, I will present a work I developed with my supervisors and colleagues from Politecnico di Torino, Pietro Cornetti, Mauro Corrado, and Alberto Sapora, which will cover the extension to dynamic loading conditions of the well-known finite fracture mechanics failure criterion. For this work, we will cover the following problem. So let's imagine that we have a structural domain, okay, a generic one, filled with a homogeneous, isotropic, linear elastic, and brittle material that is subjected to dynamic loading and boundary conditions. And so that this domain presents a particularity, a stress razor, which is here represented by capital gamma, so that we can ensure that failure will always stem from that particularity. And we will know the dynamic stress field and the release of energy upon crack propagation. In this scenario, we would like to know at which instant will the material break, will the domain break, and especially at which load will the domain break. In the literature, there are already some existing failure criteria. The easiest one is the classical approach, in which you get the maximum stress crack opening stress component, or the stress or the stress intensity factor, and you compare it against a function that depends on the loading rate. Okay, but actually this presents some problems, because it's very easy, but it's there where the problems arise, because it's a local instantaneous criterion. So for example, it cannot capture the size effect of a non-singular geometries, and also you're required to impose like a user imposed function for the relating either the strength or the fracture toughness with the loading rate. A bit more complex and a bit more developed is the dynamic extension of the theory of critical distances, in which we no longer have a local criterion. Now it's non-local, so we can capture this size effect of non-singular geometries, but still we need to impose a certain function with the loading rate. And we need to, we are adding another problem, is that we are using a constant characteristic length, so that its application for very small specimens is completely precluded. From another side, there is also the incubation time failure criterion proposed by Petrov in the 90s, which actually now is a non-local criterion, non-instantaneous. So we are solving little by little some of the problems we have. We no longer require this user input strength function with the loading rate, but still we need this constant characteristic length, so we cannot apply it for very small specimens. And we are adding complexity to the problem, because we need to obtain one extra material property, which is this tau, also called incubation time. So now what we propose is the dynamic finite fracture mechanics approach, in which we are going to stem from the following hypothesis. So the first one is we are stating that our loading states at t equal to 0. So it's completely dynamic loading. There's not a quasi-static component. And that there exist expressions for both the stress field and the energy release rate that depends only on a spatial coordinate, a spatial parameter. So it can be either the coordinate or the crack length, and the dynamic loading, and all the temporal dependence of these two parameters arise from, can be expressed through the dynamic loading. Under these conditions, we know that we say that we propose that the failure will appear at the first instant of a moment of like a set of instants that comply with certain conditions, as you are seeing now on the screen. Basically, for those of you who are aware, who are familiar with finite fracture mechanics, it's a condition minimization problem, and the conditions are one condition on the stress and one condition on the energy, so that for failure initiation to occur, we have to comply with both of these. Actually, the novelty of this approach is that we no longer compute these conditions instantaneously, but instead through an averaging of the loading in the history of the sample at each specimen. So basically, just some remarks before proceeding onwards. this minimization over time reverts of the minimization over the external force when the external force is monotonically increasing. So we get what's normally in quasi-static criteria. This integral over time is obviously performed of the history and not on the future, because otherwise it would be physically meaningless. This coalescence period, which is the period over which we are performing the integral over time, is here assumed to be a material property, but it's something to be further studied with experimental campaigns. And this property is regarded as the minimum time required for the material to coalesce all the most energetically convenient microcracks into a single macrocrack. But this doesn't mean that the time to fracture is limited by tau, just that the fracture as a fracture surface is limited to the time to failure happening in a time larger than tau. When it happens in a time smaller than tau, it will happen as a damage, so as a smeared failure. And lastly, obviously, there is a kinetic component, but it will be within the stress field and the energy release rate. So I said about the relation between the stress field and the energy release rate with the loading. It might seem a bit artificial, but it is known by some experiments that actually, when you are using the full shaping technique with the split Hawkinson bar, the following happens. So we have dynamic equilibrium conditions, and the static expressions relating the loading and the stress and the energy release rate still hold for the dynamic regime. So we can perform the following. We have the previously presented dynamic scenario. We can convert it to the quasi-static counterpart, perform some static finite element analysis to get the stress field and the energy release rate. Then we just need to substitute the quasi-static load by the dynamic load. And using our dynamic finite fracture mechanics approach, we can get time to failure, failure loading, and the characteristic length of failure. So if we go now to the experiments, for example, for semicircular bend test, we have the following. So for this case, we have the expressions from the finite elements. The loading is a ramp loading. We input this into the finite element K, into the finite fracture mechanics approach. And we will get a solution when the time to failure is larger than this coalescence period, than this tau, and another solution when the time to failure is smaller. Both conditions are just different parts of the graph, but they are continuous and smooth, as seen now. So this is for notch semicircular bend test. You can see that actually the experimental fitting is reasonably good. This is performed on granite rocks. And this is for the unnotched case. You see that at the beginning, so for low loading rates, the fitting is very good, but as the loading rate increases, the fitting worsens. Actually, we found that because to be due to the loading to the fracture surface going away from a fracture surface to a failure domain, as you can see in the figures. Okay, and just now to conclude. So basically, we have proposed an approach that sorts out most of the limitations of previously criteria. It has good agreement with experiments. Also, it's able to capture this transition from failure through fracture to failure through the damage domains. Also, the use of indirect tensile specimens, it simplifies the dynamic testing. And lastly, we also need further experimental campaigns for understanding more about the topic we are considering. So, well, thank you so much.
I think it's the one. Yeah. don't know, everything is fine. Okay, thank you. Okay. Hello, my name is Amir Mohammad Mirzai. I'm a PhD student at Politecnico di Torino, and I'm going to present a new model to estimate finite fatigue life of notch components. I will start with an overview of the model, then I present the model, and I validate it with 3 different sets of experimental data, and I finish my talk with conclusions. To start, let us consider a SN curve. It can be divided into several regions, for example, low cycle fatigue, high cycle fatigue, or finite life or infinite life. In the middle, there is a region that can be captured by a line, which firstly proposed by Basquins, and you can see here. Another assumption that I'm going to use is that I assume that the stage 2 is the dominant stage during the fatigue. So I can use the mode 1 relationship. And the final one is that I assume that the size of the plastic zone is negligible. So I can use linear elastic mechanics. The model that I'm going to develop is based on finite fracture mechanics. As Arturo said, it's firstly proposed to determine the failure load under static loading condition for brittle materials. As you can see here, it contains 2 conditions. First, stress condition, and the second one is the energy condition. And the material properties that you need to capture the failure is the sigma U, or ultimate strength, and fracture toughness. The model was extended to fatigue limit by Sakura et al. The idea to extend this model for finite fatigue life is to vary the critical material parameters, sigma C and K1F, which we call it critical cyclic stress and stress intensity factor at failure. We assume that these parameters vary as a number of cycles, and their behavior can be captured again by Basquin's equation. So as soon as we have these 2 material properties, we can insert it into the system of equations by finite fracture and determine the finite life and the critical crack advancement. Similar to the static case and the fatigue limit case, sigma C can be determined using plane samples and K1F with the crack samples. And in case we don't have a crack sample, we can use inverse calibration using a notch geometry. Here you can see a procedure of the model. So the first set of experimental data that I used to validate the model consists of different notch geometries, and the material is steel, and the loading condition is R equal to -1. It's tension compression loading condition. Here you can see the related SN data for the notch samples. And here is the estimations by the model. In the vertical axis is the number of cycles to failure by experimental data, while the horizontal one is the estimations. If a data is on this solid line, it means a perfect estimation. And these 2 lines represent the scatter band of 3. As you can see, the predictions are quite satisfactory for all the notch geometries. Here is another set of experimental data. It's the same notch samples as the previous set, plus 2 new samples under bending condition. Note that, please, that loading ratio for this set of experiments is equal to 0.1. As you can see here, the estimations here are more or less good, but it's not very satisfactory for the bending test. This can be justified by the fact that SN data are dependent on the loading condition, because I determined sigma C and K1F based on the tensile samples, while I use them for the bending cases. And the last set of experimental data that I'm going to present is based on the this set. It contains 2 different notch geometry and a notch sample with and a semicircular notch sample. The material here is inconel made by selective laser melting. Here we compared the model by theory of critical distances The left side is the predictions by finite fracture one, and the right side is predictions by theory of critical distances. And as you can see, the predictions are quite satisfactory. So to conclude, we propose a new failure criterion for finite fatigue life of notched component. The idea was to vary the critical material parameters, stress intensity factor, and the strength by the number of cycles. And we captured this behavior by the Basquine's equation. Comparison with the experimental data showed the soundness of the model, but still the work is ongoing. Here are the references of my presentation, and thank you so much for your attention. Okay.
Here we are. Okay. So, thank you, Mr. Chairman. Thank you, everyone, for attending my presentation. And yeah, maybe we are a bit late. I will try to be fast, but the ability to synthesize is not my best here. So my presentation today is about fatigue propagation in shell memory alloys, and in particular, I will show some preliminary results related to a novel energetic approach. I don't know, is something wrong? Okay. In particular, we analyzed the binary nickel-titanium system. That is a unique class of material that show extraordinary high force and shape recovery capabilities through the so-called shell memory effect and pseudoelastic effect or superelastic effect. Both these properties are due to a fully reversible solid-state transition between two distinct crystal structures, austenite and martensite, that can be activated either by temperature and or by applied stresses. However, it is well known that these shell memory alloys exhibit a very complex constitutive behavior with nonlinear hysteresis and intricate thermomechanical coupling mechanisms. And in addition, it is widely accepted by the scientific community that this transformation occurs locally, and these local effects play a very important and dominant role on material damage, especially under fatigue loading conditions. That's why we started studying fatigue and fracture of shell memory alloys a few years ago, because they exhibit a completely different behavior with respect to common engineering metals. In particular, we focus on macro crack, I mean, the one in which the size is much larger than the typical microstructural details, I mean, the grain size. And yeah, unfortunately, in that case, solid mechanics theory can be used, but unfortunately, standard theories and approach cannot be directly applied to shell memory alloys due to these complex phase transition phenomena and local effects. That's why spatial methods must be used, sometimes involving multi-scale simulation ranging from atomic to component scale. Now let me start with the core of my presentation. I will try to give a very quick overview about research activities we did in last year, and with a focus on the experimental methods and models we have developed, and finally the results on fatigue per growth with the focus with the preliminary results on the novel energetic approach we are developing. So a few information about local phase transformation. The high stress gradient, the strain gradient near the crack tip pose marked stress-induced transformation. And this stress-induced transformation have a very important effect on the wall stress strain distribution near the crack tip that have a significant effect on both fracture and fatigue properties of shell memory alloys. So these, unfortunately, these local effects are also observed under nominal uniform stress conditions shown here. And this causes also a very unusual fatigue response of shell memory alloys. So to this aim, we developed the special experimental methods. We are using high resolution digital image correlation to capture these local effects. And we are also using infrared thermography to capture the thermal effect associated, linked to latent heat of transformations. And we are also using instrumented non-indentation to capture localized transformation. About modeling, we have developed a simple model that is based on a modified version of the Irwin's correction to linear elastic fracture mechanics. It is based on the definition of an effective crack length stress intensity factor that is able to take into account the large process stress-induced zone near the crack tip. And the method is able to predict both the extent of the stress-induced transformation region, but also the wall stress strain distribution near the crack tip. So we developed also a nonlinear regression method that uses the displacement data captured by high resolution DIC to obtain effective crack length stress intensity factor by the Williams expansion series. And finally, the non-indentation, we developed special methods and parameters to predict, to capture local transformation from the nano-indentation cubes of the material. So let me move the results. We analyzed two different types of the two microstructures, basically austenite and martensite. And we use a single edge crack sample obtained from commercial nickel titanium materials. And we have also tried to analyze to capture the effects of temperature, to capture the effect of thermomechanical coupling, because there is, when increasing the temperature in a pseudoelastic material, the stress plateau increases significantly with a ratio of about 10 megapascal per Celsius degree. And okay, this is an example of the results we obtained from high resolution DIC and indentation. So we are able to capture the strain field in the near crack tip region and consequently the transformation zone. And we have observed the marked effect of the temperature on the fatigue crack propagation curves. Here you see the evolution of crack length versus the number of cycles. For the same material at different temperature, 25 to 65 degrees, there is a marked effect of the temperature, and also a comparison between the two microstructures. You can see the martensite has exhibited a much longer fatigue life. We built the crack propagation curves as a function of the effective stress intensity factor captured by our special methods. And we have observed that there is a marked effects of the temperature in pseudoelastic, but also a marked effects of the microstructure. That's why now we are looking at a different parameter. So we are trying to understand if these effects are obviously related to the material hysteresis. So in the case of austenitic material, they exhibit a fully recovered pseudoelastic response with the marked temperature effect. I mean, the stress increases with increasing the temperature. And in the case of martensite, the martensite is a pseudoplastic material. The deformations are reversible. They can be recovered by heating. So that's why we are trying to use the so-called the dissipated energy. So that is the energy within the stress strain transformation curve of the material. And this parameter can be calculated by basically two methods. A so-called global method that is from the force displacement cube obtained from the testing machine or by numerical simulation. Or the other method is a local approach that is a volume integration of in the near crack-tip region as obtained from FEM simulation. To this aim, we performed complex FT simulation by using ad hoc and fully coupled thermomechanical model for shape memory alloys. And we did this energy calculation. We compared the two results, the two methods. They are in good agreement. And now we are trying to analyze fatigue crack propagation data as a function of these energetic parameters. And from the first result, it seems that they fit perfectly the experimental data. I mean, they are able, this parameter is able to take into account the effects of temperature and the effects of microstructure. And finally, conclusion, I don't know if I have more time. So we have shown that we have observed localized transformation by different techniques. This transformation, near crack-tip transformation, are significantly affected by temperature and microstructure, and they play a very important role on fatigue crack propagation. And this parameter, energy parameter, this dissipated energy, seems to be a very good parameter to analyze, to take into account these local transformations. And as a future works, we are going to do experiment to analyze the effects of loading ratio, loading frequency, crack closure, and so on. Thank you. Can you make a paper?
Okay. My name is Francesco Ferrian. I am a PhD student at the Polytechnic of Turin. And the title of the study that I'm going to present is Size Effect through a Unified Formulation by Finite Fracture Mechanics and Quasi-Crack Model. In this study, we analyzed two different structural configurations. The first one is a circular hole in both a finite and infinite slab, while the second one is the unnotched slender beam under poor bending. For these two different configurations, we consider three different models. The first one is the well-known point method. This method requires that the normal stress over a finite distance delta must be greater than the ultimate tensile strength of the material, sigma c. The second criterion that we implemented to obtain strength estimation is the finite fracture mechanics. This criterion considers the simultaneous fulfillment of two conditions. The first one is a stress condition, and following the Le-Guillon approach, we obtain the same stress condition provided by the point method. While the second one is a discrete energy balance, and under linear elastic assumption, we can use the J-integral formalism, considering both the stress intensity factor, K1 sigma, and the material fracture toughness, K1 sigma. Finally, we consider also the cohesive crack model. Also, this criterion consider the simultaneous fulfillment of two conditions. The first one requires that the total stress intensity factor at the fictitious crack tip must be equal to 0, while the second one consider that the crack tip opening displacement must reach its critical value. For the final fracture mechanics, the two unknowns are represented by the critical crack advancement and by the failure stress sigma f, whereas for the cohesive crack model, the two unknowns are represented by the critical size of the process zone and by the failure stress sigma f. As concerned the theoretical formulation, for both configuration, stress field and the stress intensity factor can be expressed as here represented, where X and A are dimensionless with respect to the characteristic geometric size C, and where F are two shape functions. Same consideration holder for the cohesive crack model. So for both criterion, we can consider a parametric approach, and as we can see here, the failure stress and the dimensionless characteristic size gamma are expressed as function of the critical crack advancement, and here for the cohesive crack model are expressed as function of the critical size of the process zone. Here, the failure prediction provided by final fracture mechanics, cohesive crack model, and point meteor for the circular hole configuration are represented. Lower strength estimation are obtained increasing gamma, and we can see that experimental data that we obtain available in the literature are in very good agreement with strength estimation. In the second plot, the critical size of the process zone provided by cohesive crack model and the critical crack advancement are represented as function of gamma. They present a similar trend. They both decreases as gamma increases till they reach a minimum value, and they both increases as gamma increases. In this plot, the size effect for a finite dimension slab is represented. Once again, the theoretical estimation are in good agreement with experimental data available in the literature. What we did was to perform some parametric finite element analysis using ANSYS code to estimate some correction factors for the stress field and for the stress intensity factor related to a finite width geometry. Finally, we studied also the size effect for the 4-point bending configuration. Once again, the experimental data are in good agreement with theoretical estimation. For small sizes, for small value of gamma, we can see that cohesive crack model and the final fracture mechanics provide different estimation. Indeed, we obtain for the cohesive crack model a strength value equal to 3, while for the final fracture mechanic, we obtain a infinite strength as gamma tends to 0. In this plot, we consider also this master curve that we propose, and that fits very well the estimation provided by final fracture mechanics. Once again, we represented here also for this configuration the critical value of the process zone provided by cohesive crack model and the critical crack advancement provided by final fracture mechanics. Finally, to summarize, in this work, we consider two different configurations. The first one is circular hole in both a finite and infinite tensile slab, and an notch slender beam under poor bending. For these two configurations, we consider 3 different criteria: the point method, the final fracture mechanics, and the cohesive crack model. to obtain a strength estimation following a semi-analytical approach. And finally, we compare our strength estimation with experimental data from the literature. Thank you for
Good morning. I'm talking about these topics mentioned by the chairman. So the frame of this research is the aeronautic field, where, as you know, we have a combination of multiple materials, in particular metal parts for structural components, especially aluminum alloys components, and composites for especially for the shaping of profile or for other minor structural components. Of course, we also have some other complicated and complex structures like honeycombs and sandwich panels. And in general, we have different methods for joining these materials, including mechanical joints like rivets or adhesive means. And in both cases, we need to respect very stringent normative requirements, standard requirements that are related to the materials that must be qualified for aeronautic field, the testing methods, and also the fabrication process for aeronautic field that must be also qualified before. So the aim of this research is to provide some new design concept for the next generation aircraft that will be addressed to increase the environmental sustainability. And this sustainability is applied to flight operations, including, of course, reduction of emissions and optimization of weight. That means innovative structures. Also dedicated to the production phase by the shortening of the manufacturing chain and, again, introduction of coupled technologies, merged technologies with innovative design solutions. And, of course, new materials, including recycling and regeneration of materials and secondary raw materials. So the typical structure of a primary flight control structure, for example, is like this one, where you have we have metal components like ribs, spares, stringers, and so on, and other composite parts like the external skin and other minor elements. I mentioned the riveting means to join the material. So rivets have some problems. First of all, the weight on a traditional medium-sized aircraft for passengers, we have about 100,000 rivets. That means about 120 kilograms only for the rivets. That is a lot. Then also we have holes in the skin that reduces the structural integrity of the composite. A long manufacturing time to produce and join this skin, about 15-20 manufacturing steps are needed. And also the use of chemical paints and other treatments that have high disposal issues and impact on the environment. So what we are trying to do is to find a new way to build aerostructures for the new generation of aircraft. And so we started this research and innovation project
couple of months ago that is called Mimosa, multi-material airframes based on 3D joints between additive manufacturing metals and carbon fiber composites. That starts from a couple of patents we deposited at Politecnico di Torino in 2019 and 2020. After that, we built a consortium of industrial partners to find a way to provide innovative solutions regarding these new requirements. So we are the coordinators of the project. We have Leonardo as a market driver and end user of the structures, Sud that works about the regulation of the standards requirements, and a number of other technological units providing the different steps of the production. What we want to explore is the possibility to join the two materials without rivets, without adhesives, by using a co-curing method of metal inserts inside the composite. So the metal parts are fabricated through additive manufacturing processes, including shape complexity on the surface, with the building of small three-dimensional anchors on the surface that are able to grip and to mechanical constrain the fibers of the carbon fibers of the composites, and so to provide an engagement without external mechanical parts. Of course, we need a lot of intermediate complicated steps like surface coating of the metal to prevent galvanic corrosion, to improve the wettability with the composite, and many other steps. What we have here is just a very preliminary investigation about the global behavior of this kind of joint, where we have some numerical modeling based on a couple of strategies. Letter A is based on the real geometry of the joint, so 2 volumes only. The letter B is referred to another strategy with an intermediate volume composed by a mixing of properties of anchors and the composite material. Another solution is a homogenization approach. We have used for this preliminary study some material properties measured directly by experiments. On the lower part of the slide, you see a module that is corresponding to one of these anchors. In this case, is a cubic anchor. That means that we can use a modular approach by studying just one module and to, of course, repeat the effect on the whole surface. Of course, the topics of interest are, first of all, the number, the shape, the density, the orientation of these anchors, which one is better to provide the best strength of the joint. Then also the transition, the local transition of stress, strain, and the mode of force transition between the metal part and the carbon fiber, and of course the failure modes of the joint. So very preliminary experimental investigations that just to understand how much is, so the amount of force that can be transferred. So we built the metal part with additive manufacturing process on a Rainy Show machine. Here I have listed the printing parameters, and we built the joint by laminating the composite in the laboratory in an ambient condition with 24 hours of polymerization time. And we performed some static tests just to compare so the effectiveness of these models. So out of 5 samples, we get some repeatability, first of all, of the mechanical response in static conditions. We get pretty high values of the load transferred, so it's good. And also our models are calibrated, are well tuned on the experimental results. So this is just a focus on the very first preliminary investigation. We are starting the project right now, and so we will expect in the next month other results. So this is my references. If you have questions, we don't have time now, but I'm open, of course, to reply to your eventual answers. Thank you.
It's this one. I also have my colleagues for the next session.
Okay.
Okay, where do I? The other phone. Okay. Is everything okay? That's great. Yeah, sorry. Okay. Hello, everybody. I'm Simon Sedmak, and I will present the paper which was announced by Paolo related to the numerical simulation of crack growths in S275 steel welded joints with multiple defects. This is the part of an extensive research which included analyzing the behavior of welded joints which have several different combinations of defects simultaneously present, because this is a topic that isn't exactly that well researched, but could have some pretty interesting consequences in real applications. So the goal here was to use several different methods, including the experimental tests, numerical simulations using finite element method, and the digital image correlation, all to simulate the behavior or measure the stresses and the strains in welded joints with several different defect combinations that you can see here. So for the experimental basis, a number of steel plates were welded with combinations that included the most commonly encountered in practice defects like excess weld metal sagging, incomplete root penetration, vertical misalignments, and undercuts. And then specimens were cut out and subjected to experimental tests, which would serve as the base for the numerical simulations, which will be the focus of this specific presentation. Here you can see the exact dimensions for every group of specimens, and these dimensions were used in the finite element models to create them as accurate and representative as possible. Of course, this is one of the more recent stages of of the research that lasts for quite a while. We started with very simple models with just the weld metal and the parent material as the zones, and the initial goal was to obtain results that would be close enough to the experiment in terms of critical stress concentration locations, and then later we would add the heat affected zone as an individual region. We would use more refined meshes, and would also try to solve any issues that could occur, like, for example, the presence of volumetric defects, which had happened in a couple of cases. And all of this was validated by comparison with digital image correlation, which showed us how the specimens behaved during the whole tension process. And here you can see some of the initial numerical models. You can see that the geometries match what was shown in one of the previous slides, and that the finite elements were finer close to the critical areas, but they had to be additionally refined several times until sufficient convergence was achieved. And of course, now brief explanation about the heat affected zone. We didn't have the experimental results for its mechanical properties, so we used an iterative method where we sort of guessed their values based on the parent material and weld metal, and then varied them until we got the strain distribution, plastic strain distribution that would correspond to the digital image correlation. You can see one of the examples on the slide here, and these are the values that we have obtained, which were more or less uniform and a bit lower than we expected, which is probably explained by the fact that we needed a very specific welding technology to intentionally cause all those defects combinations. Here is an example of how all of the specimens from each group failed during the tensile experiment. Here, in some cases, you can see that the cracks even initiated in several different locations, which also made things somewhat more complicated, and is something that we will have to take into account in our future work. So once the models with the representative mechanical properties of the heat affected zones were obtained, the next step was to include the cracks in the locations corresponding to the ones that were determined by experiment, and to use different lengths. For this case, we went with 1, 2, or 3 millimeters. Here you can see the crack locations, which were usually near the fusion line on the heat affected zone side, which is where they occurred in the actual cases for all of the 4 specimens, all of the 4 groups. And here you can see some of the results. This is the first group with 3 different crack lengths. Here you can see that the crack would grow slightly, but would have a tendency to move towards the weld metal. And this was similar for the second group, where there was a slightly bigger increase in crack length, and also it would always reach the weld metal. And in the case of a 3 millimeter, there was also crack blunting, which I'm not sure how it's able to obtain, but that's something that we will need to consider in our future analysis. And for the third group, it was also very similar, although in this case, the crack would reach the weld metal faster than compared to the previous, because this was the one with the vertical misalignment and higher stress concentrations. Now, we could have continued simulating crack growth through the weld metal, but there was no point because that's actually not what happened during the experiment. So here the question remains why the crack always has a tendency to move towards the weld metal, when in reality it will go along the fusion line and heat affected zone, and sometimes towards the parent material, which of course were both considerably weaker than the weld metal due to overmatching. And in the case of the fourth group, another one with the misalignment, the crack path was the most realistic, and there was a significant increase that would occur until a point that for greater lengths of 2 and 3 millimeters, the calculation would stop at one point due to excess plastic strain. And then later, when this was compared to the actual behavior, there was a perfectly logical explanation for this. So the 3 millimeter model isn't even included because there was no point in pushing it that far. So, like I said, for the first group and the second group, the cracks would propagate towards the weld metal, and there would be some small increase in length. And for the first group, the stresses near the crack tip ranged from 470 to 535 megapascals, of course exceeding the defined tensile strength of the heat affected zones. And for the second group, so it was very similar, except the cracks have extended a little bit more, and there was the crack blunting for the 3 millimeter case, which resulted in very similar values. So there wasn't an increase in the stresses in case of the 2 millimeter and 3 millimeter cracks. For the third, like I said, the crack would propagate faster and would reach, and it would initiate at lower stress values because of the higher stress concentration, meaning that it required less of a load to initiate, which is also one of the main goals of our research, to determine just how much the actual stresses the joint can take will be lowered by the combination of different defects. And for the fourth group, like I said, it was the closest to the experimental results, with the crack propagating in the expected direction and its length always increasing considerably. For example, for 2 millimeters, it more than doubled and would almost reach 4.5 millimeters. And this would cause the calculation to actually stop towards the end, because it would just have way too much plastic strain, which actually makes sense when you take a look at some examples of other specimens that have failed. You can see that at one point the crack would initiate on one part of the weld, but then it would relocate to the other and continue propagating from there. So for example, these crack lengths in the weld root were limited in a certain way, and once they reached a certain length, the deformation would relocate elsewhere. And this is what has happened in the fourth group, for example. If I try to put a crack length which was greater than what was obtained experimentally, it just could not go any further because of the excessive plastic strain. Now, of course, this means that a more detailed model will probably have to include several cracks at once. And for that, I think we should focus next on the three-dimensional models, where it would actually be possible to somehow define two cracks into I don't think that there is that option yet. But also there is a few other factors that should be considered. Like Filippo Berto observed last time, we were talking about something similar. This is not your typical uniaxial tension because of the geometry caused by the defects. The specimens will deform considerably along all of the axes, and it could completely rearrange the stress distribution, sometimes causing stress concentrations in places where you wouldn't expect in normal defectless welded joints, and sometimes even causing compressive stress in certain locations.
So there is a lot of questions that need to be answered with this, and we hope that we will be able to continue in this direction with more complex model in the future. So thank you for your attention.
Okay, good morning to everybody. I am Stefano Rodino. I'm very glad to be here today to present this work about optimizing the dimensional parameter of a 3D printed active composite beam by using SMA material with a nonlinear analytical model. Here is a short outline of my presentation. In particular, I will start from the motivation, and next I will introduce some functional properties that we are interested in this work of the active composite of the active material that is shape memory alloy. And moving on the presentation, I will present some result of the experimental characterization that is needed to predict which is the behavior of this particular type of material. And after this characterization, I present the analytical model that we want to propose to predict the bending of an active composite beam. And finally, we want also to validate this analytical model by providing an analytical versus experimental result with design and prototyping phase. Okay. So this preliminary work is made in collaboration with the Stellantis group, and in particular, the aim of this project is to design adaptive aerodynamic surface by using SMA material. This is possible by using the shape morphing principle that consists in placing the active material, that in this case is an SMA material, as far as possible from the neutral axis of the section to increase the bending of the active composite. And by actuating this material, it is possible to perform a deformation of the full profile of the active composite beam in this case. This type of material, in particular the active composites, have attracted a lot of interest in the recent years because they are numerous advantages, but also you have a lot of problems, especially in terms of thermal interaction between the polymeric matrix and the shape memory material. The aim of this study is to develop an analytical model for predicting the curvature of an active composite material, and also to we want also to identify which are the best 3D printed material to product, for example, some demonstrator for this application. And finally, we want also to propose an experimental validation of this analytical model by the production of some functional demonstrator. Shape memory alloy are a particular class of material that have a different functional properties, in particular the shape memory effect and the pseudoelasticity. And this material consists in two different phases. One is austenite and the other one is the martensite. In this work, we are also only interested in one of the functional properties, that is the shape memory effect. And this property is the capability of the material to recover large deformations that are pre-impressed during the cold phase when the material is heated above the transformation temperature that is named austenite finish. To predict the behavior of this particular material, a lot of characterization are necessary, but in this work we are focused only on the to obtain the mechanical properties of the two different phases by conducting two types of tensile tests. One when the temperature is less than martensite finish, and one when the temperature is above the martensite finish. And another aspect that we are interested in is the connection between the transformation temperature and the applied stress on the SMA material. And this can be done by obtaining the phase diagram through some constant stress recovery. The first experimental characterization that we have conducted is the tensile test when the temperature is less than martensite finish. In particular, from this test, we can obtain the elastic properties of the martensite, but another important aspect is that we can also obtain the maximum transformation strain that the SMA material is able to recover during the activation. Another important test is to estimate which is the elastic module of the austenite by conducting a tensile test when the temperature is above the austenite finish temperature. Another experimental characterization has been made to conduct some constant stress recovery test. In particular, a special experimental setup has been made by assembling this setup with a thermal camera, a displacement transducer, and some hanging calibrated masses that can bring the wire to recover under a constant stress. By this test, it is possible to obtain the hysteresis loop of the material for several levels of constant stress. And from this data, it is possible through the tangent method to obtain the 4 transformation temperature for each level of constant stress applied. From this data, by interpolating this data, it is possible to obtain the phase diagram of the material. And with this phase diagram, we have all the relations that connect the transformation temperature to the applied stress. Okay, at this point at the end of the experimental characterization, we have discretized an active composite beam that is composed by a polymeric matrix with a defined number of SMA wire in itself in a bimaterial plate by using the relation 1. At this point on this section, it is possible to apply the momentum equilibrium and the non-interfacial debonding between the SMA layer and the polymeric matrix layer. And through this relation, it is possible to connect the stress generated during the recovery of the SMA material directly to the bending radius of the active composite beam. And from this relation, it is possible to obtain the tip vertical displacement of the active composite beam. At this point, we are not only interested in the vertical displacement of the tip, but we want to reconstruct all the deformed profile of this active composite beam. So for this purpose, it is necessary to apply the linear elastic beam theory, but this theory cannot be applied to materials that are not homogeneous on the section. So an homogenization of the section is needed, and the height of the section is maintained constant to preserve the strain distribution. At this point, we know from the previous relation, which is the value of the vertical tip displacement, and we can evaluate which is the load through this relation 1 to bring the beam at this vertical displacement. At this point, by varying the coordinate x along the length of this active composite beam, it is possible to obtain the full deformation of the beam along the full length. This model have to deal with large displacement, so it is necessary to evaluate also the horizontal displacement of each point of the along the length of the beam. The beam has been subdivided in different interval, and for each node, the vertical and horizontal displacement are calculated through the relation 2. At this point, to validate the analytical model, a first comparison has been done by taking some parameter from the literature. When I talk about parameter, I mean geometrical and mechanical parameter of the SMA material and the polymeric matrix, and also the dimensional parameter of the active composite beam. And by doing this, the model was fully implemented in MATLAB. And the first comparison, it is possible to obtain by comparing the stress generated in the SMA layer with a good agreement. Another type of comparison can be made on the vertical displacement of the tip of the beam. In particular, both the literature result and the analytical model that we have implemented show a maximum tip displacement for this geometry of around 30 millimeter with a maximum transformation temperature of 100 Celsius degree. Another comparison to validate the model has been made by using the experimental parameter that we have obtained for the experimental characterization that I previously talked about with a new geometry. And in particular, this parameter has been implemented in the ANSYS software, and the comparison has been made in terms of the deformed profile of the active composite beam. And also in this case, a good agreement of the analytical versus the numerical model is. And finally, the last comparison that we have made is based on experimental validation. In particular, we started by analyzing some 3D printed material by conducting different 3-point bending flexural test, and in particular we selected 3 of this material that have an elastic module under 2 gigapascal, and in particular PETG, polypropylene, and PVDF. And by doing this, we have directly inserted the SMA wire during the printing process with a protection with a microtube of Teflon between the surface of the polymeric matrix and the SMA wire. The prototype produced we have not obtained a good result from this prototype because all the material present an incredible delamination problem, and this is due the thermal increase in temperature when the SMA wire has been activated. And to solve this problem, we have redesigned a new active composite produced as 3D printed material. In particular, we introduced some intermediate support and terminal that are printed in carbon fiber reinforced nylon, and the base of the beam is made by PETG. And we have used in this time a special class of SMA wire that are silicon sleeved to insulate the SMA layer between the polymeric matrix and the SMA wire itself. Okay, it's the last one. At the end of this, here there is a video, but I think it's not work because there is the laser. Okay. Okay, so we have measured the deformation of this produced active composite beam, and we have compared the result versus the analytical mode with a good agreement, in particular with the maximum transformation strain in the analytical model of 5%. In conclusion, we can affirm that when we want to design active composite beam, the temperature play a really important role in the design of this particular type of material, and also the SMA material set the maximum transformation, the maximum target temperature needed for the actuation between the dependence on the stress, and also we have to choose correctly, which is the electrical current if we want to provide a joule heating not occur in an overheating, for example. Okay, thank you for attention.
Under 87. Yeah, this one. Yeah. Yeah, thank you. So hello, my name is Mario. I'm from Portugal, and I'm studying materials engineering at the University of Porto.
Today, I'm going to present you ongoing work about the dissertation of completion of a master's degree in engineering. This study will focus on the fatigue behavior of a high-strength steel welded connection under rotating bending. First, I'm going to start with a small introduction and motivation for this work, followed by the methodology used for the specimens tested. Then I'm going to share and discuss with you the results obtained from the fatigue test, and at the end, the conclusions and talk about the future. Governments nowadays are aiming for the decarbonization of the energy and the economy in order to achieve a more sustainable world. And for that, they are focusing their attentions on the more clean and renewable energies, such as wind turbines. Since Portugal, these installations are located offshore. These structures are made from thick steel sections connected together through welding techniques. And since we are talking about offshore installations of this, there are some type of cyclic environmental loading that leads to cyclic stress known as fatigue. And fatigue is the main property that leads to catastrophic failure of this structure. Also, since we are talking about welding techniques, it's important to understand the three main sections and zones of a welding connection. First, we have our base metal and the welding material, and the welding material by the filler material used in the welding process. And then we have the heat affected zone. The heat affected zone had some type of changes in the microstructure due to heat input of the process, such as grain size crossing, secondary phase formations that leads to some type of changes in the mechanical properties of the material. For the experimental parts, two 30 millimeter thickness plates of quenched and tempered S690 steel were connected together through metal active gas welding process, and Corwell 69 was used as the filler material for the welding process. From the welded plates, two main sections were cutted, A and B, and from these two main sections, longitudinal and transversal cuttings were performed by abrasive water jet cutting techniques. From each section, 25 spaces, being 16 of them for the base material, 4 for the heat affected zone, and the other 4 for the. Here you can see the technical plan, and also you can see the section A and section B, and the morphology of the specimens tested. As red arrows, you can see the specimens representative of the heat affected zone. And as blue arrows, you can see the specimens where the most shortened section intersects the welding material. The rotating bending fatigue test was performed under a fatigue stress ratio of -1 and a frequency of 23 Hz. Here you can see a schematic representation and the fixed location of the specimens on the rotating motor, and also the added mass that will attend as a submitted tension. Also, you can see the maximum bending stress expression represented. The first type of results obtained from this test is the Euler's curve, also known as SCN graphics, that correlates the number of cycles until fracture of the specimens with the stress amplitude applied. For this test, a 10 million cycle fatigue endurance limit was stipulated, so any sample that reached this value was considered as a runout. Here you can see the mean curves for both slice A and slice B for the results obtained from the base material. And by the determination coefficient here presented, we can prove that the statistical model will provide a good outcome of the results. Here you can see the mean curve for the results of base material and also for the heat affected zone and welding material specimens. It's important to notice that we have a small for low cycle fatigue test, and this is to increase with the number of cycles of our. Now for the mean curve of the section B zone of this section, we can see the same problem with a heat affected zone results, but it's worth noting to talk about two specimens that can be outlier. The first one is for the base material, and this one had some type of residual magnitude to some type of handling of the welded plate, the manufacturing process, and with the analyzed many offers to refer that magnetism tends to increase the fatigue resistance of our material compared to the other ones for the same stress amplitude. The other one is also for the base material, and this one at a lower resistance compared to the same samples for the same stress amplitude, and this can be due to some be presented inside of the microstructure. Further same ADS analysis, we can have some about this specimen. Here we can see all the specimens, all the results from all the specimens of SSB and heat affected zone and welding material. This was noted a limited number of specimens from the heat affected zone. We could only apply to the tensions only for 500 and 480 the heat affected zone and welding material space. By dividing the standard deviation for 520 megapascal, we can see that we have a lot of dispersion weld material in the heat affected zone due to the heterogeneity of the microstructure in this. For 400 megapascal, this doesn't happen because we have a higher number of samples that reach the maximum but dangerous limits being considered as runout. The results for these stress amplitudes are not that dissimilar compared to 500. The second analysis that we made was surface structure analysis, and we can see here, for example, for the base that we have a nucleation site at the bottom left sample, and we have another nucleation site on the top right, and we can see that of the propagation of the crack. That is the second main step of the fatigue endurance. This marks the nucleation site, and as we can see here, we have the final step. That is the catastrophic failure. There is a representation of a more brittle surface of the specimen of our sample. Also, it's worth noticing here that we have a middle section that has some different type of roughness. This roughness is from the this ductile zone is the material trying to behave itself against the fatigue loading, and this is represented by the so-called dimples. Also, since the filler material for the welding has more ductility compared to the base material, we can conclude that the dimples for the magnification of the same analysis are way smaller material compared to the base section. To conclude, it's important to note that the fatigue behavior actually depends on a high variety of factors such as surface finishing, residual stresses, and another type of material defects such as porosities and inclusions. The variation heat affected zone areas, and also the dispersion results due to the non-regular area of our plates. As future works, we are going to analyze and compare the microstructure and the evolution of the microstructure, and we'll compare it with the results of the fatigue test obtained in order to evaluate dispersing crystallographic orientation and the secondary phase particles. And also we are going to compare it with the profile of the longitudinal section of the house. Also, we are going to evaluate the influence of the process in a 60 millimeter thickness plates during the manufacturing product of our plates. And at the end, we are going to compare the fatigue strengths of our curves with those in the standards. I would like to acknowledge also the project, the 4.0, and thank you for the opportunity and thank you for your attention.
Ah. Sì, ma devo... non c'è qua. Torno. Mm? Allora, questa è nella prossima sessione. Ok? Forse no. Eccolo qua, perfetto. Shop, ok. We can upload it. You uploaded them? Yes, but I have to upload it on the other folder. Which one? Folder IGF27. This one? Okay, so. Okay. I have already. Ah, you have. Because we have uploaded it in the previous photo. Sì, un attimo. EGF, this one, no?
Yes.
This one, and
Both.
can I take this? It's better. It's better than the PPS. Thank you. Dariano? Probabilmente ho dato la ricevuta ieri, ma non ricordo. Perfetto. Possiamo chiudere. No, è che non la riuscivo a afferrare, che mi scivolava. Lei deve caricare, presentare, sta qua per vedere un po'. Non ci riesco. Devo mettere il numero di presentazione. Di presentazione, come che funziona? Devo caricare due. No, è un editore. Ok. E questa che è sezione 2? Dimmi, perché...
Ecco poi nulla.
Non
conosci nulla?
No.
E ogni volta non ci subito da descrizione di quando.
Remove it set. È proprio.
Messo un commentario?
Sì. No, a me questo qua. Sì, sì, lo conosco. Sì, 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 lo conosco.
Beh, questa siamo veramente un mercato nero.
No?
Ma devi
Due?
un po' dietro avanti. Oggi che vedi? Venerdì, due.
Sì, c'è.
Che la gente chiude la cartella.
È un po' labile. Vabbè, ma tanto non stiamo usando. È acceso?
Qual è? No, l'altro. Devo caricare anche questa?
No.
Sì.
Sì.
Stanno video? Ti serve questo?
No.
Se c'è video, se non ti serve il laser, ti consiglio di non mettere il puntatore laser, perché altrimenti dopo non ti parte il video. È il primo?
No.
Allora, chiudo. Sì, prendo pure questa porta cortese.
No, non so se poi rispettano quello che hanno comunicato. Io quando facevo il nome del lavoro, cito tutti gli autori, qualcuno si presenta.
Branislav Georgievich. Thank you for the introduction. Yes. Once again, thank you for the introduction. My name is Branislav Georgievich, and I come from the Innovation Center of the Faculty of Mechanical Engineering in Belgrade, and I will show you a comparison of two recent approaches to ductile to brittle characterization of ferritic steel developed by our institution. Some of this team, some people are also involved in this research and are not listed here. I will be short and concise as much as possible. So, sorry. Beside the presentation of the basics of these two developed studies, approaches, I will show you the demonstration of application of these two methods using the Eurofracture data set of this ferritic steel, as you can see on the screen, in the function of the stress intensity factor in the index of JC at the temperature, and the data set results at the -60 degrees. As you can see, this is the ongoing research, and this is the paper that need to be that is a part of this research. So let's start with the first 1-point method.
as you can see, it uses Weibull statistic and is based on the Volin research. Since I have a limited time, I will not go deeper into the problem and the basis of the Volin research. As you can see, based on the smaller CT specimen size, we predict the behavior of the larger CT specimen size. And this method is an economic one because it uses only one pair of data set that is used for the prediction, the behavior of the larger CT specimen size. As you can see, it uses a regression analysis, and one of the variable parameter beta is size independent and is fixed. So let's switch to the second two-step scaling approach. As you can see, it is based on the two-step scaling as illustrated on the figure on your right side. And two premises are shown here, equation 1 or 2. In this approach, we imposed a shape function based on which determine the beta and dependence of beta and shape function is sigmoid, and I don't have a time to explain this, maybe later. So let's switch to the demonstration of application of first method. As you can see, the method, the demonstration, the application starts with the fitting of the experimental results of the smaller CT specimen size. In this case, we CT 25. Based on these results, we did a prediction, estimation of the prediction, estimate of the behavior of the probability of failure of larger specimen size using this equation. You can see the parameter of Weibull CDF. Here you can see the CDFs of the probability of larger CT specimen size. As you can see, this method is more, how to say, a rigid one, and a conservative one. For example, for KJC of 100, the probability of failure is much larger than the experimental results, and this feature is pronounced with the increasing CT specimen size. So let's switch to the second approach. It uses two pair of data set. We need two pair of data set to predict larger CT, the behavior of larger CT specimen size. This method starts with a fitting of experimental results. Here you can see Weibull parameters. Then we did, this is the mathematics for the prediction. For the prediction, in this case, of CT 100. Then we determine the beta. In comparison to the first model, beta was fixed. Here, this is not the case. So this is the Weibull parameter for the larger CT specimen size, in this case for CT 100. As you can see, this prediction is more realistic. It's not so rigid, and in comparison to the first one. So to conclude, I think you saw the two methods, approaches for the prediction of structural toughness. First approach is more rigid, and from the point of the structural integrity standpoint, it is more safer, but is expensive. It's not economic one in comparison to the second one, which provides more optimizing feature in designing of the structure based on these results. And further direction of this study will goes in the how to say, in the study of sensitivity of the size of the data set, based on which we will predict larger structure. So this is it. Any question? Thank you.
Okay, presentation on this one. Yeah, first. Okay, hello everyone. My name is Ana Petrovic. I am assistant professor at the Faculty of Mechanical Engineering, University of Belgrade. My colleagues and I were dealing with structural integrity of a pipeline, including welded joint. You will see later what that implies. But firstly, we performed, sorry. Can you help me, please? Okay, thanks. We performed inverse methodology in order to obtain mechanical properties of all three regions of welded joint. As you all know, you have base material, you have weld metal, and you have heat affected zone, and they all have different mechanical properties. So in order to obtain their mechanical properties, tensile testing of specimen containing welded joint was performed. In the picture on your right, you can see stereo cameras. Loading was filmed using stereo cameras, and the results were analyzed using RAMI software, which is based on digital correlation method, digital image correlation. Digital image correlation implies it practically compares photos in undeformed and in deformed stage. And so displacements are measured and deformations are computed. So you can obtain the whole deformation field, as you can see in figures on your right. Here you can see welded joint with defect. It doesn't have much with this that I will tell you later, because this inverse methodology is just a small part of overall ongoing study and ongoing project, which deals with welded joints and welded joints with defects, without defects, welded joints and corrosion. So this is just a small part of that. Here you can see a crack propagation filmed using system RAMIS, but to come back to our inverse methodology. In picture on your right, you can see a deformation field in a moment when plastic deformation occurs. And so we have the force and we have the deformation in that moment. And we used that to improve our numerical computational models. So we used those deformations and that force, we applied it on our numerical computational model. And we had some, at first, characteristics of the material are orientational. We did know characteristics of the base material of weld metal so-so, and we didn't know anything about heat affected zone. So we improved our numerical model. We changed those characteristics when deformations of the numerical model and deformations of our specimen, our experimental results were the same. We said that's it, and we got numerical properties, material properties of the three zones. So it was iterative approach, and we got those properties, and we decided to use that information to improve our computational model of a simple pipeline. As you can see here, pipeline is a good starting example because it is loaded with internal pressure, and the stresses are mostly membrane stresses. So the three numerical computational models are developed. The first one is the simplest one. It is the one without solid joints. All of us would model some construction in that way when we are planning to do some linear elastic computation or some linear elastic analysis. And the second and the third one included welded. But in the second one, heat affected zone have the same properties as the base material. And in the third one, all the properties obtained using inverse analysis were applied to that model. So those are properties that are obtained from inverse analysis and that were included in those calculations. As far as linear elastic analysis, the same. And that is one more confirmation for us to, when do linear elastic analysis, we can just model a pipeline without welded joints in a way that we all do practically. And why all the three models are the same? Looking in this diagram, you can see that all three materials have practically the same modulus of elasticity. So it is expected to behave in a linear elastic analysis for them to behave the same. But in nonlinear analysis, the situation is completely different. Here you can see a start of plastic deformation for the first computational model. And of course, it is more interesting to compare the second and the third with the first one and the second and the third one to another. And as you can see, the second, once again, the second has heat affected zone with the properties same as base material. And the third one, in the third one, all three zones have their own properties obtained using inverse analysis. And I think that the third model is something closest to the real behavior of a pipeline, including welded joints in nonlinear analysis in the plastic, when plastic deformation occurs. Internal pressure that caused plastic deformation is in the first column, and estimated stress concentration factor is in the last one. As you can see, stress concentration factor decreased when heat affected zone real properties are included into calculation. But that's not the only important thing. Stress gradient, as you can see from the table, stress gradient is completely different And those are completely two different constructions. Practically, their probability of failure index is completely different. Their work life is completely different. So the significance of knowing real material properties of heat affected zone can be clearly seen from this analysis. And in the end, I would like to thank you all for your attention. And if you have some more questions, some further questions, you can send me an email or ask me now. Okay. No, it was really simple. It was practically iterative process in which we changed a little bit and a little bit and a little bit while deformations were the same. I think that it could be do in some more clever way, but in this case it was done like this. Thank you.
Thanks everybody for coming here. Today I'm walking you through the identification of LADAD curves, combining logistic regression and maximum a posteriori estimation. Consider this kind of metallic specimen which retains defects irrespective of the manufacturing process. And if we test several of these, spanning many loading conditions and characterizing the size of the defect where the fatal fatigue crack occurred, we get this plot, for which we assume working within linear elastic fracture mechanics, defects regarded as cracks, Murakami's length as the characteristic size of the defect, and the mode 1 stress intensity factor range as the fatigue crack driving force. Amongst many models, LADAD curve allows assessing the fatigue endurance limit, considering the presence of defects. And the LADAD curve is the black solid line that separates the regime of propagating cracks and non-propagating cracks. The equation of this curve is this. Okay. It's overlapping. This one is overlapping. Okay. So ask me about the equation. I'm not cheating. Don't worry. Well, delta KTHLC, you see on the right is the fatigue crack growth threshold for long cracks, while delta sigma W is the fatigue endurance limit of a defect-free specimen. And somehow these two parameters should be determined. And over the years, many researchers has developed many models to do so, but these models require complex experimental calibrations and basically neglect the previous results from the literature. And needless to say, populating this graph is such an onerous endeavor. No one so far has attempted to determine this curve using the sole data we see here, only the markers, the points, and the crosses. And that's our goal. Let's move to the case study. We consider this literature data set that regards this aluminum alloy. These are the fatigue testing conditions. And the gray line is the reference LADAD curve, whose parameters are these. The former was identified by fatigue crack road tests, while the latter was extrapolating by these authors from their model, essentially. But let's pretend not to know the gray line. And I gotta say that the defects pivotal to structural integrity are concentrating around the mid region of this graph, because those on the leftmost side are far too small, whereas those on the rightmost side, well, we hope there aren't any such big defects, okay? And potentially, I might draw infinite LADAD curves, but how can I determine the one that optimally splits this data set without characterizing the entire spectrum of defect size, only using with this data at my disposal and assessing the error of the evaluation? Let's see. Let xi and theta be the tested sample and the vector of trainable parameters. The LADAD curve essentially tells us that specimen above the curve should fail, whereas those beneath should run out. And this actually is a typical machine learning binary classification. That's our idea, however. We think that the probability of failure should increase as we are moving upward away from the curve, and vice versa for runouts. So this failure probability should be linked to the sign distance of a point to the curve. And that's where logistic regression comes in handy, because it squashes these distances into the interval 0, 1, thus returning probabilities. Normally, logistic regression is trained via maximum likelihood estimation, which entails building this likelihood function and maximize it. This is the likelihood of this data set. And the parameter of the curve that optimally splits the data set are supposed to be located at the maximum of this function, where the maximum exists. And so this approach in this case wouldn't work. But we can notice that an hypothetical optimizer will be naturally attracted to the yellow region, where the log likelihoods steadily increase around 180 megapascal. And such an intuition suggests that the data set could be almost perfectly split by an horizontal line at 180 megapascal. And what about the other parameter, the delta KTHLC? Well, we examined many papers where other estimates of this parameter were available for similar materials as well. And we encode this prior information using maximum a posteriori estimation, which relies on Bayes' theorem. Posterior equals likelihood times prior over the evidence. And taking the logarithm of both sides, we end up with the log posterior that has to be maximized. By the way, the log prior was derived by assuming independent distribution for each parameter, but still the user can prescribe in principle any distribution over these parameters. That represents our prior belief over these parameters. Let's assemble the log posterior. This is the previous log likelihood. And exploiting the evidence separation of the data set, we let the data dominate as far as delta sigma W goes. And we prescribe a prior that vanishes during maximization. Conversely, regarding this parameter, we gather the results from the paper I mentioned earlier into this normal distribution. Summing these two colored contribution, we get the log prior. And if we sum these contours, the result is really, really cool. Now, the log posterior does have a maximum where the optimal parameters are located. And differently from maximum likelihood estimation, which provides only point estimates, the maximum a posteriori gives the joint probability distribution of the parameters. And marginalizing it out, we can retrieve each distribution for the parameter. And the mode of this parameter, the mode of this distribution, leads to the evaluated El-Haddad curve in black, which is the optimal one. And also this concurs well with the reference in gray we've seen before. Sampling the posterior distribution of the parameters, we can generate numerous El-Haddad curves in a Monte Carlo fashion and calculate the prediction interval for a confidence level of, for instance, 95%. And we get the lower and the upper bound of this prediction interval that can be interpreted as the failure probabilities at 2.5 and 97.5%. In particular, the lower bound can be interpreted as the probabilistic fatigue endurance limit for this material and can be used in engineering practice design. That being said, we are ready to wrap up. Logistic regression models the binary classification of the El-Haddad curve, maybe inconclusive when trained via maximum likelihood estimation and only provide point estimates. Conversely, maximum a posteriori encodes intuitions, hypotheses, and prior knowledge from the literature while training logistic regression and provides interval estimates, according to which we compute the prediction intervals using a Monte Carlo approach, and we can calculate the probabilistic fatigue endurance limit so that this can be used in probabilistic engineering design. You can email us for further questions, and I also invite you to visit our research group website. Here we go.
This one. Nothing's happened before. Okay. Good morning, everybody. I'm very glad to present our work about the evaluation of aerodynamic and structural performance of active composite driven by embedded small wires. This work is in collaboration with the group Stellantis, and the aim of this project is the design of active aerodynamic surface to increase the efficiency of the vehicle. In particular, we start talking about the SMAP properties and our thermomechanical characterization, the design of our prototype, and the test of this prototype, and our conclusion, of course. For the beginning, I want to talk about the functional properties of this particular material. In particular, we can talk about the pseudoelasticity or shape memory effect. We want to use the shape memory effect to realize our prototype, And this effect consists in the recovering of residual deformation presets on this material, in particular on this wire, through the thermal activation. As we can see on the graph, the properties of this material is very related to temperature and stress applied. For this reason, we must do some tests to understand how these parameters are related. And in particular, we construct this setup to acquire the load applied on the wire by an hanging mass, the linear transducer to register to acquire the displacement, and a thermocamera to acquire the temperature on the wire. Thanks to the Joule effect, we can activate this wire and register and acquire the load displacement of this wire. These are thermoelectrical test. Also, we can see after 20 cycle, around 20 cycle, the characteristics are stabilized, and we acquire the last cycle as shown in the figure. This is the thermal curve, the heating and the cooling curve. And thanks to a tensile test, we can evaluate the mechanical parameter such as the Young module, and we can we can construct the phase diagram. Okay, starting from this data, we develop our prototype as shown in figure. And this prototype is made by a plate as an elastic element made by a PC plus PS material and a silicon material to isolate the wire from the environment, and to terminal aluminum end part to crimp the wire. Okay, after the design of this element, we carried out some virtual tests thanks to the program console and the geomechanics module, in which the small wire was treated like a bar present inside the reinforced concrete. In this software, the SMA behavior are modeled by the Lagudas model, in which the parameters is the same of the test of before. Okay, we can see our prototype in function, and this with no load applied. And in the second video, we can see how the pressure of the wind affects on the plate in terms of vibration and deformation. And we can conclude that the pressure and the stress applied obviously on the wire change the shape of this element. And we must compute with coupled physics simulation the effects of the wind. To define the pressure on this plate, we use also already console, and we define a control volume to simulate the wind tunnel. And this is our test in the wind gallery. And in conclusion, we see that the model predicts well the behavior of this element with no load, and for thermal problem of dissipation, we can improve our model, but the deformation is very similar. For future development, we want to install our device on a vehicle and test them to understand the efficiency. Okay. Okay. Thank you. No. So,
Can I get the pointer? Thanks for the introduction. It's a pleasure to be here, and I'd like to welcome you to my talk. I want to present some early results regarding an unexpected observation during my main work, focusing on very high cycle fatigue regime regarding the influence of the vibration behavior and the resulting fracture surfaces of two high-strength steels. I'd first like to start with a brief introduction regarding the used test setup, as well as the specimen geometry, and obviously the tested materials. Then I'd like to show a basic comparison of this observation of the differing resulting fracture surfaces, then followed by a roughness measurement of those surfaces using confocal microscopy, and showing the differences in surface morphology. I'd like to conclude with an actual comparison of a natural frequency and ultrasonic amplitude data during the fatigue test. So schematically shown here is the in-house built ultrasonic test setup consisting of a piezoelectric converter, 3 boosters, and the specimen shown on the right. All the parts, including the specimen, are designed in such a way that the displayed longitudinal standing wave is formed, with the maximum stress being found in the center of the specimen. All the tests were performed with a load ratio of R-1, with a nominal testing frequency of 20 kilohertz. The ultimate number of cycles were 10 to the power of 9. And to avoid a significant self-heating of a specimen, the pulse pause mode, the tests were performed in a pulse pause mode, and additional soft air cooling was used. The tested materials were both quenched and tempered high-strength steels, 52-100 and 40-140, with a martensitic state, resulting in the given hardnesses. And the main difference is the significantly lower fatigue fracture toughness of a 52-100 when compared to a 40-140 steel. Displayed here is the fracture surface of a 52-100 specimen, failing at an internal non-metallic inclusion, and a smooth fracture surface area around the so-called fisheye is observed. Outside of this fisheye, we see, as expected, a forced fracture with a crack ridge height increase over the crack propagation. So to put it bluntly, this surface is pretty much straightforward. However, in case of a 40-140 steel, while still observing crack initiation at the non-metallic inclusion in the inside of a specimen, and still the formation of a fisheye, contradictory to the 50-100 and very unexpected, we observe several beach marks as well as a heterogeneous fracture surface area, which is hardly observable. We have an alternation between a brighter, a darker, a brighter, and a darker area in the bottom of this picture. To actually make those differences more tangible and quantifiable, we performed the roughness measurement along the crack path in 7 profiles, with the average roughness being displayed on the right with the dotted lines. Overall, as expected, we see an increase in average roughness with distance to crack initiation and a relatively large scatter. To reduce the scatter and actually get more robust values for the average roughness, we also did a circular measurement circular roughness measurements, and the results are displayed here. Like I said, as we expect, we increasing roughness with increasing distance to crack initiation, and we were able to reduce this the scatter. We did the same, we performed the same procedure for the 4140 steel, with the results being displayed in blue. While still observing an increasing trend, most strikingly, in the darker areas close to the final fracture, we observe significantly lower roughness measurements in both measurement directions, comparable to the roughness inside the fisheye. To now get to the actual reasoning behind why we observe such roughness deviations between the two specimens, we observe the surface fracture morphology. Starting again with 50-100, we have a grid of SEM images on the left, with their respective positions being marked on the right. So inside the fisheye, we observe a rather smooth fatigue fracture surface, while outside the fisheye, we observe a ductile force fracture with dimples or honeycomb-like structures. Overall, increase in surface topography roughness is observed, resulting in the increasing roughness shown before. However, in case of a 4140 specimen, while still observing a rather smooth fatigue fracture surface inside the fisheye, and also the beach mark in the brighter areas, for example, see image E, we observe an intergranular force fracture. Most strikingly, we see an alternation between an intergranular force fracture in the bright areas, followed by a fatigue fracture with a relatively smooth surface area. And we see an alternation between those different fracture surface morphologies. Just simply based on the linear elastic fracture mechanics model, we would actually expect an increase in stress intensity factor, and therefore not this alternation between force and fatigue fracture. Shown here is an excerpt of actual generator data during the failure. Again, starting with 50-100 specimen, displayed is the power as well as the frequency and the amplitude. The pause times between the post-pause modes were cut out. So each of those blocks corresponds to one impulse with roughly an average of 5,000 cycles. We also observe a similar pattern for the power, as well as a nearly constant frequency, as well as maximum amplitude during the whole test. However, if we zoom in close to the failure and actually have a look at the natural frequency as well as the amplitude, we observe a sharp drop in natural frequency as well as amplitude. If we calculate the area of the fisheye, or if we measure the area of the fisheye and then calculate the maximum stress intensity factor using Murakami's law, as stated or as seen in the presentation before, we see that the actual value of the maximum stress intensity factor at the border of the fisheye corresponds very well to the fracture toughness, therefore resulting in unstable crack propagation and resulting also in the continuous fracture surface seen above. However, if you do the same for the 4140 specimen, while still observing nearly constant values throughout all of the tests, if we zoom in close to the final fracture, we see a much slower and more prolonged decrease in natural frequency as well as amplitude over several pulses. Again, while measuring the area of the fisheye now touching the surface, so we have to account for surface defects, and calculating the maximum stress intensity factor at the border of this fisheye, we see that the fracture toughness of the 4140 material is not reached, therefore resulting in a much slower decrease of natural frequency as well as amplitude, actually influencing the formation of a fracture surface. So with an increase in defect size, we would increase the area of the fisheye. However, due to the drop in natural frequency, we also reduce the amplitude, and therefore we get this alternation between force and fatigue fracture. So as a conclusion, we can summarize following points. Depending on the material, either an abrupt or a slow and prolonged decrease of the natural frequency and amplitude are observed. Therefore, the unstable crack propagation and this defect size resulting in the amplitude decrease seem to compete with each other. And the critical defect size seems to exist where, at which the natural frequency as well as the amplitude drop significantly. If a fracture toughness is reached before this critical defect size is formed, no influence on the amplitude decrease on the late crack propagation can be observed. However, if the fracture toughness of a material is higher, and therefore the critical defect size is reached before unstable crack propagation is actually started, the crack propagation is significantly altered due to this amplitude drop. I'd like to thank the colleagues from Karlsruhe Institute of Technology for the manufacturing of the specimens, as well as the German Research Foundation for funding of the main project. And obviously, I'd like to thank you for your attention. Sure. Yeah, it was quite fast. Well, we are actually working to mean the direct correlation between the drop and the fracture surface marked, let's say. Yeah, it's visible. We also have some assumptions, but we're still working on it, and we want to actually increase the data acquisition because we're at the moment we have a data acquisition rate of 1000 Hertz, which is quite troubling if your excitation frequency is 20 kilohertz. So there is a correlation, but we are actually still working on FEM simulations as well as experimental results with artificial defects. So give us some more time.
Non lo devo condividere. Se poi ti serve sopra, se adesso c'è scritta qui 6 problemi, la puoi spostare in alto.
Okay, good morning, everyone. Thank you, Professor Ferro, for the introduction. I'm Daniel Suarez, and a PhD student from Politecnico di Torino, and I want to present this work in the influence of biochar in cement paste and mortar specimens. First of all, I have to talk about the Portland cement context, in which every year more than 4,000 million tons of cement are produced, consuming huge amount of energy, mostly produced from fossil fuels, emitting 1 ton of carbon dioxide for each ton of cement produced, contributing with more than 5% of carbon dioxide emissions. Meanwhile, some alternatives are soft. For example, supplementary or alternative cementitious materials and manufactured nanomaterials, in which these materials have been used to improve the mechanical properties of cement-based materials or to improve the durability to obtain long-lasting structures. But the question is, we have only these cases, for example, like fly ash or silica fume or carbon nanotube. To answer this question, I have to first talk about the waste context, in which only in America, more than 30% of the food produced there is wasted, and they generate also more than 70 million tons of food waste. Here in Italy, Italy produce 20 million tons of food waste and 3 million tons of food waste. Why I'm talking about this? Because we are generating biomass. To solve this situation, this problem, biomass has been treated to produce energy, or it can be treated to produce energy, and there is a new problem, or maybe a solution, the biochar. What it is? What is it? Sorry. It's a solid material that it's produced after the thermochemical treatment of biomass to produce energy. And this process, should be, or the most common ones are pyrolysis and gasification, and has been used mostly in the agricultural sector, but several researchers have found that it could be used as a filler to, like silica fume, for example, to improve the mechanical properties of cement-based material. So we can use it in the construction. Why? Because it's a porous material with a large surface area that can absorb water. It's chemically stable inside the cement matrix, and it's made of carbon, more than 90% of carbon. So it's a carbon-based materials, like for example, carbon nanotubes or carbon fibers, not the same one, but it's a carbon-based material. But the most important thing is a waste, and we can use it inside the cement matrix to improve the mechanical properties, as I said before. And for going to the experimental part, we use a Portland cement type 1, water, surplus plasticizer in the case of cement paste, standard sand for mortars, and biochar, of course. Specifically, we use two types of biochar. Borgotaro one, that is generated, both of them, are generated in Italy. Borgotaro was obtained through gasification process, and Neta biochar was obtained from pyrolysis. Both mixes were first to begin with the mixes. We first mix the biochar inside the water, and then the whole mixing process was complete of making 4 batches, beginning with 0% of biochar inside the mixes, 1, 2, and 5%. After 28 days of curing, we performed two tests: the 3-point bending test to evaluate the fractal strength and fracture energy, and the compression test to evaluate the compressing strength. In the 3-point bending test, we used a Japanese standard, and to the compression strength, we used the Union 196 one. Moving to the results, we can see how the biochar particles can improve in almost all the cases the fractal strength property of cement-based material, cement-based specimens and mortar specimens, being the case with when 2% of Neta biochar was used, arriving to an improvement of more than 80%, and in the case of mortars, obtaining almost an improvement of 10% more respect to the reference one. Moving to the compressive strength, the trend was more or less the same, reaching in some cases, for example, in the cement-based material, all the same percentage, the 2% one, reaching an improvement of more than 60%, and in the case of mortar, arriving to more than 50%. And the last part is the fracture energy. This could be the most promising results, because in the case of cement-based specimens, we almost reach more than double the capacity of the reference one, reaching more than 150% in the first stages, which means 1% and 2%, and more than 240% more for when 5% of NEDA biochar was used. And in the case of mortars, we are improving to 20 and 25% when 2% of 5% of NEDA biochar was used. It could be seen also that in overall, Borgotato biochar has now the same capacity to improve the mechanical properties as NEDA biochar could do. And this may be because by the process that we use to obtain the biochar. In literal, it's possible to see how the pyrolysis process could be a more suitable to obtain a biochar that can be used for construction materials. To conclude, we can say that employing biochar inside the cement-based material could facilitate a sustainable production because we're using a filler material that is a waste in almost all the cases. We are conserving landfill space when we are valorizing the due to carbon dioxide emissions, and we are improving the mechanical properties or cement-based materials that usually are fragile materials, and we can see in the factory energy, we are improving the toughness of these materials. And of course, more future studies have to be performed to obtain more knowledge about this filler. Okay, thank you.
So it's a real pleasure to be here. Exactly 14 years ago, I was standing there discussing my master thesis in this room in civil. And now I'm happy to talk about something about fatigue cracks. So I think for your community, this is quite common. Here are some common facts. So you have a crack initiation. So this is the rough description of a fatigue failure. Then you have a stable crack propagation. And finally, the fast fracture is usually described by Griffiths or phase field models that are essentially a regularization of Griffiths' theory. And what we are interested in this work is essentially the Paris regime, where you may observe a stable fatigue crack propagation. And what I realized in a certain moment of my life, which was in civil engineering, you do not study very well fatigue as a material effect, is that fatigue is a boundless research field. So if you look into Scopus for papers with a keyword with fatigue in the engineering and mathematical domain, you get hundreds of thousands of documents. And then when you start to look into phase field plus fatigue, the first works came out around 2018. And then when you go further and you look into titles, papers with in the title, both Griffith and fatigue together, no documents came out. And therefore, new ideas came from this thinking on this matching, Griffith and fatigue. The fact that
typically brittle fracture models and fatigue models for nucleation and propagation, as Wöhler curve and the Paris law, are disjoint. And so the question, how to describe, how to update Griffith structure theory and phase field theories with ability to describe fatigue cracks. To capture fatigue effects, that is to promote crack propagation growth cycles, in green here, you may think in increasing the driving force, like increasing G, keeping GC, the fracture toughness constant, or the other way around, you may think to decrease the resisting force with the load cycles, keeping G, the driving force constant. And the second way is what I found more natural to do. And so the idea is, how can we achieve this reduction? So the question was this. And let me introduce another fracture toughness, called here fatigue fracture toughness, that is a degradation of the monotonic fracture toughness through these three ingredients. So Xi is somehow the fatigue variable, so the phenomenon that is responsible for fatigue effects. Phi is the fatigue history variable, and D is the final function that is a decreasing function when the fatigue history variable increases. So to understand these three ingredients, you may think on tires degradation and energy. So you may think, for instance, the fatigue variable as the position of a car, Phi, the fatigue history variable, for instance, as a total traveled kilometer, what you see on the dashboard typically, and it's the integral over time of your speed, and D as a function which tells you when it's time to change your tires. So when D reaches the value 0, this is time to change the tires. And so this modeling strategy was applied between 2016 and 2020 in the phase field context. But then we start to focus on Griffiths plus fatigue, in particular this paper, which you're invited to refer to for the details of this presentation. Here you may, so the approach applied to, so this modeling strategy applied to fatigue seemed to work. For instance, I maybe just show you one video, if possible. So you apply this strategy to phase field fracture, and you see a fatigue crack propagating due to load cycles. And the same has been applied, for instance, with plasticity. So you may see on the left the equivalent plastic strain, on the right phase field evolution, the fracture evolution. So even for coupled problems that seem to work. So you see starting localizing plasticity and promoting at the same time crack advancement. But you may see some results of the phase field model matching quite well Paris law. Paris fatigue crack regime was we were able to describe. We were also to provide a unified model for describing Wöhler curves and the fatigue crack regime. And we provide also a mesh intensity model. Nevertheless, there were still some issues in these phase field models, like an L-dependent fatigue response, where L is the internal length regularizing the phase field model, and no full control on Paris parameters. What were we doing? We were starting from Griffith with a direct formulation, typically with a monotonic load, switching to a variational formulation, thanks to the contributions of Frankfurt and Marigot, where the crack is not anymore prescribed by small l, but it's an unknown of the problem, gamma. The crack path could be arbitrarily, totally arbitrary. And of this problem, we have a regularized formulation with the phase field. And what we did was, at the beginning, endowing the phase with the capability of fatigue by changing the fracture toughness to fatigue fracture toughness. But is this the correct path? Maybe not. Maybe the correct path should be this other one. First, one should endow Griffith with fatigue effects, and then provide a regularization of this model. And this is what we have done and what I briefly will show you now. Classical Griffith equations are here on the left, becomes the one on the right, just the replacement of the fracture toughness with a state-dependent fracture toughness. In terms of generalized standard materials, this means means to take a state-dependent dissipation potential. So the blue one is the standard dissipation potential for Griffiths. And you see as phi increases, the history variable increases, you have an decreasing of the dissipation potential and hence of the fracture toughness. With Griffiths in a pure linear elastic framework, I will show you just a very simple example. You take as fatigue variable the elastic energy density, in particular the singular part, as a fatigue history variable, something more involved, and then as fatigue degradation function, a simple decreasing function. G inside which defines the history variables has been split in 4 contributions, each of one dealing with a specific feature of the model. For instance, G1 is responsible to deal with the singularity at the crack tip. And let me point your attention on G3, which is able to model mean load effects, and G4 to tune the Paris exponent. So just take a very simple problem, an infinite plate with a single crack, and a K cyclic loading, just vary K. The final goal was to find the Paris law, the delta L, delta K extension in a stationary regime. And so the plane model with G3, G4 equal 1, 1 were able to recover Paris law without mean load effects, or at least very small sensibility to the mean value of the stress intensity factor. Taking G3 with not with exponent 0 but 1, so that it has a contribution, we are able to recover essentially Foreman's law, a mean load effect, and playing with G4, keeping G3 equal 1, we are able to link the exponent of this in this G4 function with the Paris law exponent, and this has been what we have done. Midterms goal provided a variation extension of this, improve the phase field model, and also explore acceleration techniques for computations. Long-term goal would be in this approach to include non-proportional mixed loadings, tactile fatigue, and other multi-physics effects linked to temperature and environment. So I hope you have enjoyed the one. Yes, an example. This was within the phase field formulation, but you may think the same. In that case, the fracture toughness was not decreased only by the elastic energy, but in particular by the dissipated plastic energy. So it was the accumulated plastic strain through its and the related dissipation that was in this case degrading the fracture toughness and hence promoting crack. Yes, the most simple framework is Griffith linear elasticity, so without plastic modeling, and this is the way of describing a crack, a fatigue crack. Of course, if you include then other ingredients, you may enhance the model in this way. Right.
Thank you, Mr. Chairman, for the introduction. And I will present on this work called the recent developments regarding the use of the SD method to finite element software. With this work in particular, with Professor Berto, we wanted to provide some recommendation for a simplified use of the SD method by investigating all the parameters that can influence the error by applying this method to a procedure that we call it the volume-free procedure that we have investigated before only in a numerical matter, but in this work we are dealing with it in an analytical matter to investigate all the parameters. So first of all, I will give a brief introduction about the strain energy density method and what is the basic concept of this method and the theoretical framework. And after this, I will explain the volume-free procedure and how we have found some recommendation for its application in order to acquire the SD value with low error with respect to a more conventional procedure. The energy method is a local approach, an energetic local approach that is validated for to investigate both fracture in static condition and static failure. And the failure criterion that this method is considering is essentially that the brittle fractures happen when the local strain energy density averaged in a given control volume reach a critical condition that, assuming an ideally brittle material, can be also estimated starting from the UTS of the material according to the equation that you can see here. The critical value of this strain energy density is assumed to be independent of the notch opening angles, the loading condition, and the local geometry. But I've said that this value must be averaged in a control volume, and you can see here what are the characteristics of this control volume. In particular, it has a shape that is slightly changing between the local geometry, because if you look at the sharp notch here, you can see that it is a sector-shaped cylinder, while for a blunt notch, it has a crescent-moon-like shape. Even if the shape of the sharp notch would be considered just a special case of the shape of the blunt one. The position of the control volume is changing with respect, depending on the loading condition. If we consider a sharp notch, this will be centered with the stress singularity point. While if we consider a blunt notch, this will must be aligned according essentially to the mode 1 dominant concept. The control volume is also characterized by a characteristic length that is considered to be a material properties, and it can be evaluated from the material properties in the loading condition. In here with load condition, I mean static or dynamic load, according to the equation that you can find here. First of all, let's see a bit the theoretical framework of the method, starting from the stress field of the in the vicinity of the crack of the tip of the sharp V notch. We can derive some equation to describe the strain energy density field, as you can see here, and in particular, this equation we have developed during the frame of this work, also this equation. And in order to evaluate the strain energy density value, it is needed to integrate the energy over the control volume. In this case, for the sharp notch, you can see here the description of the integration domain. And according to this, it is possible to derive some equation that are linking the strain energy density, the strain energy density value with the strain density factors. And here you can see some equation that we have derived in order to evaluate the strain energy density value, starting from the notch stress intensity factor with changing both notch opening angle and the Poisson ratio. while these were only available before in not with an analytical exact solution. What I wanted to highlight also here is that, as you can see, the value of the strain energy density is a function of the different notch fatigue intensity, notch factor, stress intensity factors. It's a function of the notch orbiting angle, the control volume radius, but also of the shape of the integration domain that it is considered. Some consideration about the method. There are some drawbacks that are essentially that for the application of this method, considering that you need to average the energy density value in a given control volume, you need to partition the model somehow to evaluate this value. And dealing with more complex geometries, it is actually needed to apply the method according to conventional procedure to different simulations. This, of course, is a drawback for the method. On the other side, we can see also that there are a huge advantage of the method, that is that this method is characterized by very low sensitivity to mesh refinement. Considering these drawbacks and disadvantages, we developed the procedure for applying this method that we call the volume-free procedure, that wanted to overcome the need to partitioning of the Smith element model in order to calculate the value. We want to keep the STD low sensitivity to the mesh refinement, and we want to avoid the two simulations to apply the method for blunt notches. As you can see here, the procedure is quite simple. Instead of modeling partitioning the model to have the value of the strain energy density averaged, we consider a selection of the elements that can approximate the control volume shape. And we have seen that the difference that is given by the different procedures actually a function of just the ratio between R0 and the mesh size. But there are some assumptions that I want to explain here. Making the assumption that the total energy stored in each element is computed directly, directly through the stiffness matrix and the displacement field, and that the area of the elements in the control volume is calculated exactly, but also that the theoretical control volume shape cannot be described exactly by a Smith element method. We have the essentially that the error achieving in evaluating the average strain energy density depends only on the approximation of the integration domain. In order to investigate better the volume-free procedure that we had proved only through a parametric numerical study, we have found an analytical model to describe the selection of elements inside to describe the control volume, as you can see here. And there are some assumptions, of course, and are that the outer elements of this selection are considered perfect equilateral triangles, that the elements centroid one vertex of the elements and not tip lies on the same line, and that the elements centroid of the outer elements centroid have a radial coordinate equal to the characteristic length of the R0. As you can see here, the value of the strain energy density evaluated in this modified control volume integration domain is still a function of the notch stress intensity factor, the notch opening angle, of the shape of this integration domain. Doing some analytical calculations, we can see here that the difference between the strain energy density value averaged in the theoretical shape to the integration domain and the difference in this modified control volume is a function of the ratio between the notch stress intensity factor, the geometry, and this ratio between R0 and the mesh size. By doing some numerical integration of the all the equations that I showed before, we can see here the results in terms of difference between the strain density values evaluated in the modified control volume and the one evaluated in the theoretical control volume. First of all, we have seen that the influence of the Poisson ratio is negligible. After that, if we consider the maximum and the minimum values of this difference between the two values, we can see that, as a matter of fact, if we consider the difference given by each of the single loading modes, and it is actually a weighted average between all difference of the single modes considered alone. And as a matter of fact, we cannot end up with an error that is higher than the maximum error that each model on has. And considering also only the maximum of this error with changing the notch geometries, we can find that there is one value of the ratio between the and the mesh size above which we can be sure that the value of the strain density that we are considering is lower than a certain error. This, of course, because we didn't want to assess to determine exactly the error between the two different procedures, but we wanted to achieve an easy recommendation for the applicator of these methods. We have done this also considering a different control volume shape, and this is actually the results for the volume shape that one will achieve, also considering the conventional procedure to apply the method. And of course, in this case, we have seen that the error is decreasing much faster with this ratio R0 on the mesh size. And it's indeed, as you can see here, that we have reached an error lower than 4%, already with the ratio of 2. You can see here also some validation with some values that we have found in literature investigating the error of the strain energy density method. And as you can see here, the errors that we found in literature are fitted quite well by the analytical model that we have proposed. But in any case, you can see still a variability in the results because this is due to the assumption that we have done at the beginning, because first of all, we didn't consider the higher order terms in the formulation, of course. And because when you are having a model that is too much coarse, of course, the energy in the stored in the elements is not cannot be exactly defined, exactly calculated. With the conclusion of this work is that we have derived some new exact analytical equations used for the application of the SED method, starting from the not stress intensity factors, and or also to determine stress intensity factors starting from the SED method. And we have proven the volume-free procedure in an analytical way, showing that the only parameter that should be considered is the ratio between the R0 and the mesh size. And finally, we have defined some modeling recommendation in order to apply the method, achieving an error lower than 4%. Thank you for your attention. Yes. Okay. This is an idea that we were evaluating. The problem, in my opinion, maybe because essentially, if one starts with the DAC measurements, it could be possible to somehow determine the strain energy density value. But my concern about that, be honest, is that the problem is to achieve the exact deformation in a very narrow spot. So probably you will not be able, probably, to get the deformation in that tiny spot. Typical size for R0, it will range from 0 to 0.5 millimeters. You know, I was just wondering about the perfect.
Vediamo qua. Sì. Perché la sì. Questo? Sì. Questo.
Good morning, everyone. I'm Franco Maria Di Russo, PhD student of the Department of Mechanical and Aerospace Engineering at La Sapienza University of Rome. And today I will present my latest work, that is time analysis of nitty rotary endodontic instruments to fatigue stress conditions, a study of the influence of geometrical parameters and design optimization. Endodontics is a dentistry discipline that deals with the study and treatment of cavities inside the tooth. The cardinal treatment, called root canal therapy, involves the removal of dental pulp when infected due to caries. Caries formation, in fact, is a degenerative procedure that, in the most extreme cases, can lead to tooth loss. Instrumentation of endodontic canals is done through the use of rotating devices, usually conical, which are intended to extract infected tooth tissue. Currently, endodontic instruments are made of nitty alloy, and this has contributed to a profound technological innovation compared with traditional steel instruments. Characteristics that have made nitty alloy so suitable for making rotary endodontic. So basically, the characteristics that made this type of alloy particularly good for the production of this type of tools is basically to three reasons. That is biocompatibility and shape memory and super elasticity. And basically, we have that shape memory properties and super elasticity properties are related to the crystallographic phase of the material. And we have that in the case, the nitty alloy has martensitic phase. We have shape memory properties, while in the austenitic phase, it shows super elasticity properties. The advantages over traditional still files are related to the simplification of operating procedure due to an increasing of rotational speed during therapies, a predictability and effectiveness of the treatment that is related to the conical shape, that is a sort of property extremely related to the type of alloy used. And then we have a reduction in endodontic treatment time. These devices, however, are subjected to significant stresses that can lead to intraoperative fracture of the instrument. The main causes of fracture are torsion failure, which occurs when the instrument encounters an obstacle that constrains the tip, and the most coronal portion of the instrument continues to rotate and fracture occurs, and the fatigue accumulation, that is an inevitable consequence of the accumulation of alternating tensile and compressive stress. This is basically caused by the rotation of the instruments into irregular curvilinear geometry canals. On this slide, we can see a couple of images taken by SEM analysis, in which we can see the fracture surface on the buff case. And we can see even that that has a different shape, because in the case of torsion, there is a sort of centripetal development of the fracture, while in the cyclic fatigue there is like there is like a separation of the planes, of the crystallographic planes. The purpose of this study is to investigate the influence of some geometrical parameters in the fatigue behavior of different type of endodontic instruments. Three phases are identified, that is flexibility analysis, fatigue analysis, and design optimization. In the table, you can see like the geometric features of these three types of instrument under consideration, and these are selected from the most popular endodontic instruments on the market. They have a different cross-sectional geometry, but they have other parameters that are similar. The material model adopted in this study will be unique and will refer to Auricchio model, which is held in high regard in this type of study. The first simulation analysis is aimed to define the attitude of each tool to bending. Flexibility and cyclic fatigue strength are two characteristics that have been shown to be directly related. This is because they both depend on the ability of the alloy and of the tool to resist tensile and compressive stresses due to bending. The definition of the boundary condition was conducted taking inspiration from the studies mentioned in that slide, and involved this to the application of a fixed support at 3 millimeters from the tip and a 9 millimeter displacement to the tank. These are the results of the following analysis and are reported in terms of equivalent von Mises stresses. Maximum values are recorded. Maximum values recorded for each instrument are shown in the table, while through the images it is possible to observe how these stresses were distributed along the axis of the instrument. In all these three cases, the area subjected to higher stress is the one at the interlocking constraint. Next, the same devices were subjected to more relevant conditions to analyze the fatigue phenomenon. In this case, the devices are induced to fit inside a curved shaped canal, that is basically a simplified representation of the real tooth canal, and then to rotate. Again, previous work was taken as a reference for defining the boundary condition. A translation of 15.5 millimeter was imposed on the endodontic instruments. Following it will be constrained to rotate 360 degrees. The results in this case are reported in terms of equivalent von Mises stresses and total strain. Unlike the previous case, the simulation were conducted through the application of two consecutive time steps, each corresponding to the application of a load condition. First the translation, then the rotation. The output results are calculated through the test, which allows the evolution of the stress and the strain state to be evaluated through the analysis. In terms of equivalent stresses, the instrument that demonstrated a better result is the wave 1 gold, followed by the reciproc, and then we have the wave 1, which demonstrate these two, the reciprocal and the wave 1, demonstrate a similar behavior. In terms of total strain, however, the best one is the wave 1, then we have the wave 1 gold and the reciprocal. The wave 1 gold that is basically making a comparison of the result of the first analysis, the flexibility analysis, and the fatigue behavior analysis shows best results. So was then subjected to a design optimization process aimed at defining an optimized geometry that could provide greater fatigue life. 4 geometric parameters were considered, that is the diameter of the tip, the diameter at 4 millimeters, the diameter at 12 millimeters, and the helical pitch. The 3 diameters were parameterized because of a study inherent the influence of the taper of the instrument. The wave 1 gold is a variable taper instrument. Specifically, there is a taper of 7% from the tip to 4 millimeters section, 6% from 4 millimeter section to 12 millimeter section, and then we have 3% from 12 millimeter section to 16 millimeter section. Before moving on to the actual optimization procedure, it was appropriate to conduct a study on of the influence of the selected geometric parameters on the mechanical behavior of the instruments that are evaluated in terms of total strain. A set of 10 possible values was given to each parameter centered on the value of the commercial instrument, and its influence on the overall mechanical behavior of the instrument was evaluated individually. From the graph shown on the left, it is possible to guess how, as the values of the parameter increases, an increase or decrease correspond an increase or a decrease in terms of equivalent total strain. From this influence analysis, we select a set of 3 values for each parameter that is centered on the optimal value, and through that values, we implement a design optimization procedure in which we studied like 81 set of parameters, and the results are shown in the table, in which we have a comparison from in terms of equivalent total strain and fatigue life between the commercial instrument and the optimized one. And basically, we have that fatigue life grows from 288 cycles to 385 cycles. The fatigue life has been calculated through the adoption of the Kaufman-Manson criterion, that is a criterion that deals with oligocyclic fatigue. So at the end, we made a preliminary study regarding bending properties of commercial endodontic instruments with different cross-sectional geometry, A mechanical strength analysis of the same instruments under sliding and rotational conditions within a simplified root canal was conducted. Then a study inherent the influence of the geometrical parameters on the overall mechanical behavior of the endodontic instrument was conducted. And finally, a design optimization procedure was made with the aim of increasing the fatigue life of the instrument that performed best in the previous 2 analyses. Future developments is to substitute the singular curvature root canal with a double curvature root canal, and then the aim is to use a real root canal. And obviously, these results will be compared with experimental results. Thank you so much. For sure, yes, we are developing like an electromechanical system which that we are going to use for an experimental analysis of these results. Both torsion and fatigue life. Thank you. Thank you very much.
Morning, Giacomo Fretta. I'm a researcher of the Department of Civil and Industrial Engineering of the University of Pisa. And today my talk will be about the IGF assessment of additive manufacturing in notch specimen in increment 718, considering the effective local geometry. What we will see? We see, first of all, a methodological part consisting in theoretical methods, practical graphics analysis, that for what we are dealing about can be considered as a methodological part. We see our results, our data, experimental data, so the SN curve, and then we see our finite element model to understand what happens in the material during the fatigue test for our specimens. So we have material, as I said, well-known increment-based alloys, increment 718 for selective laser melting application. We printed the material using the Orange 4M500E printer installed at the laboratory of selective laser melting laboratory of the University of Pisa. All the specimens were built in vertical direction. The layer thickness was 60 microns, and we employed standard process parameters, so the parameters suggested by the manufacturer. We will study the fatigue behavior of this specimen in the as-built surface conditions, so no post-treatment was applied, no in terms of heat treatment, but most important, not in terms of machining the surface. We had actual loading cycle fatigue test. We tested smooth specimen and notch specimen with a notch angle of 90 degrees and notch radius ranging from 0.3 to 2 millimeters. That means concentration factor from 1.6 to 3.3. We tested the specimen in load and loading direction, a stress ratio of 0.5, so repeated load. Then we tested with a remote measure machine frequency of 150 Hz. If we take a look to the microstructure of our material, we are dealing with a material that has structure. We have a density that is almost 1. We have only some small unavoidable gas and trapped bubbles, but we are dealing with a material that, apart from the typical features introduced by the selective laser melting process, has no defects inside. If we now take a look to the outer part of the specimen, so the geometrical part near the notch of our specimens, here we have an example of the 0.3 notch specimen. We see in the right, in the left top image, we have the full picture, and then we have a magnification part in the other image. On the right, magnification image of the center of our notch, where you can see and how irregular is the effective
notch geometry compared to the smooth radius that we added in our CAD model. And then if we take a look to downskin and upskin part, we see that in the upskin portion, we have a smooth superposition of mercule that create a very smooth surface, while in the downskin part, we have a more irregular stacking of mercule that are more irregular in terms of the external roughness, but also if you see to the dark marks that point out to the black marks that point out to the boundary of the downskin part. We have very irregular. In the downskin part, we have irregular mercule in terms of the outer surface, but also in terms of the stacking. So what we observed after our isostatic test in terms of fractographic analysis, so our fracture surface, we had fracture crack that had their onset from the fracture surface, from the external specimen surface for all the tested specimens, from both for the smooth one and for the notched one. But in the case of notched one, usually we have ratchet mark because we have different planes of initial crack propagation, and then during the propagation, the two different planes join together with the ratchet marks. If we see to the position of the crack, crack propagation surface, as it's well known in the literature, in a notched specimen used by selective laser melting and testing in this build condition, the fracture propagation plane is moved toward the downskin surface, not in the central part of the V-notch, as is typical from machine specimen that is pointed out by nominal Phi models. We see that for all the specimens, here you see plot where the position from the V-notch apex is divided by the notch radius to having the same picture both R2 and R1 specimens. We see that there is a constant trend, almost 10% of the height of the notch towards the downskin surface. It's evident also if we see some test results fracturographic from fracture surface on the center part from different specimens, not from like the one that is contained, but other specimens that we tested, where you can see that the fracture propagation plane is moved towards the downskin surface, with some irregular case where the roughness is enough also to have multiple fracture propagation planes with something that starts also in the downskin part of the so with as-built notched specimen, we have the fracture propagation plane that is not exactly the one that we can expect from nominal specimen. So to understand this, we created our finite element model, dealing axisymmetrical model because we deal with round specimen. We created both a nominal geometry model, usual model for dealing with notches, but also a model that takes the information from the metallographic examination of the real notch geometry. It was extracted outer profile of the specimen in the notch part. This profile was inserted in a specimen geometry, introducing only the portion of the real notch, so the external roughness and the actual geometry of the notch, both in terms of deviation from the nominal geometry and local roughness. And we solve both these two models. So let's go to our data. If we see the SN curve, so the fatigue data, we see that both the introduction of the notch simply moves towards the bottom, so to low stress the strength of the material, but all the curves result to be almost parallel with a low notch sensitivity that is with a Q factor that is from 0.16 to 0.30, but with lower values in the case of the blunter notches. So the R2 specimen is really similar to the smooth one, meaning that probably the roughness effect are really important. Now, if we introduce the average strain energy density approach with a control value determined from the standard theory of the method of 0.21 millimeters, we see that this method pretty effectively
rationalize the data that are condensed to our master curve, you can see that there is still a scatter between almost two master curves, the one of the R2 and the R1 specimen, and the one of the R0.3, 0.5, and the 2 specimen that are coincident by theory of the method. And probably this is an effect that can arise from different roughness and different notch geometries. So method effectively condensates, but we are not still able to create a really unique master curve. If we go to see what happens when we have the nominal model that you see on the left part of the image for each of the two figures, and the actual specimen profile in terms of longitudinal stress, we see that we have the stress map that is almost similar between the nominal and the actual specimen. So the external force and the global distribution of the stress is not so much affected by the real notch geometry, but the maximum value of the stress is strongly affected. We have that the effective stress concentration that we have at the maximum, the highest value of the set that we can see here is almost double than the value obtained with the nominal model. And this maximum value is located obviously in surface irregularities, like the one you see here on the towards the upskin, the downskin surface of this 0.3 notch segment. If we introduce the average strain energy density theory also in this model dealing with the effective notch geometry, here you can see the control volume from on the left image you have the nominal geometry. On the two images on the right, you have the effective two examples of the effective geometry for 0.3 and 1 millimeter of radius notch. And here you can see that it's not dealing with effective geometry. It's not so straightforward to locate exactly the center of the control volume and the position, as Pietro well explained before. And now, if we go to see what happens in terms of average strain energy density within the control volume, we see that we have, even if we have the highest value of the stress, much more higher value of stress in the actual profile, when we go when we average the strain energy density within the control volume, we see that the ratio of the nominal average strain energy density compared to the effective average strain energy density is almost similar. We have value of about 1. We need to further increase our statistics so understand exactly the dispersion of the data, but it's almost 1. We have here an example also with R1, where on the right image we don't have the same scale, just to point out where is located the maximum of the strain energy density value, even if the average value is almost the same. And what were our just to take home messages? We see that selective specimen in a specific condition have a low notch sensitivity. We see that average strain energy density method pretty well rationalize the fatigue behavior of notch as the manufacturing specimen, and that this value resulted to be not significantly influenced by local surface irregularities, meaning that with industrial components, we can use the effective with the nominal geometry with an elastic model to deal also about effect related to local surface irregularities without the need of a more complex model that is the one that we presented before. Thanks. Yes. Yes. This is one of the things that we have to improve, because I studied a lot of sections extracted from a very wide bunch of specimens. So we tested several sections, and then the average value, when I say the dispersion is between different sections, but for sure it would be better if we had something. No, I had simply sectioned it. So I sectioned several specimens with different depth. But yeah, for sure, a micro-CT image or having a 3D profile could enhance our results.
Questo? Devo condividere lo schermo. Thank you, Mr. Chairman. As you know, infrared thermography has been adopted in the past 30 years to assess the fatigue properties of materials. And in the last 10 years, more than 10 years of research, the evaluation of the energetic release under a static tensile test has been adopted also to analyze possible irreversible plasticization in the materials. So the aim of our work is to move from the uniaxial stress field to a biaxial stress field. So we perform both static tensile and static torsional tests for a structural steel under adiabatic condition. And as you know, here is reported the classical Resitano thermographic method to assess the fatigue properties of the materials. But as I say at the beginning, in the pioneeristic work of Cagliotti since 1982, the energetic release has been monitored during a static tensile test. And as you can see here, we have a linear decrement of the temperature reaching a minimum point, and after once this minimum point has been reached, the temperature increase. Historically, this point has been considered the yielding point, the yielding stress level of the materials. But if we analyze this region, we can retrieve some useful information about the damage of the materials. So in 2009, Resitano proposed the static thermographic method to assess the first damage initiation within a materials. So during a static tensile test, we can see that the temperature of the specimen undergoes to a linear decrement of the signal temperature, then in a linear way according to the Lord Kelvin law. Then the temperature experience in a second phase a deviation from the linear trend up to a third phase where the minimum temperature point has been reached, up to and the final phase here where the specimen broke. As I say, point B is related to the yielding stress level of the material, but if I am able to detect the change in the slope, so the change between phase 1 and phase 2, I can correlate this stress level to as the macroscopic stress level that introduced the first damage within the material. So I can think that this first damage can induce fatigue damage if cyclically applied. Actually, we are also working to a machine learning approach to detect the transition point between phase 1 and phase 2. Here there is a publication on fracture and structural integrity. So moving to our work, we adopted hourglass specimen of a structural steel and we test 3 specimens per test. I mean static tensile test and static torsional test, adopting 3 stress rate, 3 megapascal per second up to 5 megapascal per second. We analyze also the maximum point of a rectangular area positioned over the reduced section of the hourglass specimen. And we adopted a biaxial load machine and an infrared camera with an acquisition rate of 15 Hertz. So here I report the temperature signal versus the load. As you can see in the first phase, in the fractional test, we can see a linear decrement of the temperature followed by a second phase. And here in this point, we can see that there is a net step between the temperature signal, because here we experience Luther's band on the materials. The same applied to the torsional stress state. So if I filter the temperature signal, this is for the tensile test. Here I can see that there is a first phase, as I mentioned earlier, and a second phase with a different slope. If I perform the linear regression of these 2 phases, I can assess the intersection between these 2 lines, so I can read the limit stress of the material. This is performed for a stress velocity of 3 megapascal per second. Here I reported also the temperature curve for 4 megapascal per second and 5 megapascal per second. The adoption of the stress rate is important in order to highlight the phenomenon, because it must be performed under adiabatic test conditions. So the specimen mustn't have the time to exchange it with the surrounding environment in order to appreciate the phenomenon. Moving to torsional test, we can see for the 3 megapascal per second test that we can also see 2 different distant phases, the first one and the second one. And here also we can estimate a tangential stress, a limit tangential stress. The same applied for an higher stress rate, 4 megapascal per second, while it is a bit difficult to assess the distinction between the 2 phases in the highest velocity, 5 megapascal per second. Here I reported all the test results. As you can see, we have the yielding stress both expressed as normal stress and tangential stress. And here I reported the limit stress assessed both under traction and torsional tests. So in conclusion, we can say that the structural steels exhibit the typical trend of a thermoelastic load, and it exhibits also the transition point between the phase 1 and phase 2. Also in the biaxial stress rate, we can appreciate the phenomenon. And we can, in further study, we have the idea to perform on the same specimen geometry fatigue test both in monoaxial and biaxial stress state to correlate the limit stress with the fatigue limit of the material. Thank you for your attention.
I would also invite you to the special issue on forces in mechanics regarding energy method, and for PhD, the summer school in energy method and fracture that will be held in Messina in July. Thank you.
Mi sembra strano.
Ma ti serve momentaneamente? Ah, no, perché quello ce l'ho pure io. Un attimo, mi tolgo subito. No, mi devo solo scaricare la presentazione. Mm? Ah, vabbè, scusa, non puoi aprire direttamente da lì il microfono. Oh, ciao. Va bene. Ah, io presento e lo rivolsa. Ciao. Sì. Allora, questo è il mio, sono il secondo, giusto? Sono diventato il primo. Vado anche in bagno. C'ho secondi.
Sì, se lei era Scusate, ma abbiamo aperto il microfono.
Hello, everyone.
Good afternoon. We can start this in the context of the symposium on the mental and intellectual of traditional materials. I would like to tell you that each speaker and maximum of 8 for the whole presentation and 2 minutes questions and comments. The first lecture is of BIM in structural behavior occupied with the titanium landscape SRP structure and its intensified to the
Just a moment. So we can start. So, good afternoon. I'm Costanzo Bellini, and I'm presenting this work that is a part of a wider activity about these hybrid titanium lattice FRP structures. And this is a project that is carried out between, these activities are carried out by our group at the University of Castellino and Southern Lazio, and another research group from the Italian Aerospace Research Center. In this work, we have analyzed the in-plane bending properties of these kind of structures. And here you can see the steps followed in this work that corresponds to the content of this presentation. First of all, we have defined a case study. So we have defined the geometry of the short beam to be tested and the materials to be considered for this test. In fact, we have considered 2 different kinds of FRP for the skins. Then we have produced the specimen. It's a 2 steps factoring process. In fact, first of all, we have produced the core of the structure made of titanium, and then we have added the skins made of FRP. Then these tested have been, these specimens have been tested considering the 3-point bending test. And finally, we will analyze the results. This is the presentation of the results. First of all, the case study. So the cell, the lattice structure that has been chosen is the octet truss cell. This cell is composed by a face-centered cubic cell composed by 24 trusses. As we can see in the figures, they are in a gray color. And inside this cell, there is another cell, rhomboedric one, composed by 12 struts and is in red. The size of the cell is 6 millimeters, so the edge of the of the tube is 6 millimeters, and the diameter of the truss is 1 millimeter. As concerns the specimen, the length of the specimen is 30 millimeter, and the length of the core of the specimen that corresponds to the length of the specimen is 30 millimeter. The width is 10 millimeters, and the thickness of the core is 9 millimeters. But then we have added the skin, and the thickness of the skin is 1 millimeter. So the total thickness of the specimen is about 11 millimeters. Then the materials considered in this work are, for the core, commercial alloy, titanium, aluminum, vanadium alloy, while for the skins we have considered a carbon prepreg and an aramid prepreg. We have paid attention to choose a commercial grade prepreg presenting the same kind of resin. In fact, the resin is the ER450, that is the same for both prepreg considered in this work. Then, as concerns the manufacturing process, first of all, we had produced the cores of the specimen by using the EBM process, the electron beam melting process. This to produce the core. First of all, we have realized the CAD model of the core itself. So we have defined the cell in a specific software. Then we have prepared the EBM printer for the run for the production of these cores. The EBM is a process that is based on the powder bed technologies. And so we have filled the reservoirs with fresh powder. Then we have started the machine, and the machine, in an automatic way, was able to produce the cores, the structures, the cores. Then the block containing both the specimens, the cores of the specimens, and the powder was taken out from the machine, and the specimens were cleaned from the powder. In fact, this is a powder bed process. And here in this image, we can see the produced core. After the skins were bonded to the produced core. So first of all, we had to prepare the layer of prepreg, and these layers were stacked together with the core, the produced core. Then and together also with the adhesive. Then this stack was put in the vacuum bag. The vacuum bag was closed and heated in an autoclave for the curing of the prepreg. Finally, at the end of the process, we cut the specimens from the produced bars. As we can see here, these specimens are quite long, so more than one specimen to be tested was extracted from a single bar. And here we can see some examples of the produced specimen. The test considered for this work is the 3-point bending test. Here we can see the scheme. The particularity of this work is that the skin is parallel to the loading nose direction. The distance, so the span between the supports, was 20 millimeters, and the loading spin considered for this work was 2 millimeters 4 minutes. Here we can see the results. I have reported just a curve for each type of specimen. We can see that both material presented a similar trend. In fact, there is a first linear load increase, so a sort of elastic behavior, that is followed by a first breakage of fibers, and after this breakage we can see that the trend is no more linear. Then the maximum load was reached, and this maximum load is almost the same for both specimens, and it is followed by a sudden load drop. Then there is a short segment of residual load capacity, and the load capacity is a bit different between the two specimens. And finally, there is the final breakage with the load that tended to zero. As concern the analysis of the fracture, we can see that in the case of the carbon fiber hybrid structure, we can observe that on the lower part of the specimen, we can see a sharp fiber fracture, tensile fracture, while on the top there is a wrinkling of the specimens, of the fibers. For the other specimens, we can see the same conclusions, but the difference is that the fracture is not so sharp, but there is a sort of frying of the composite material in the lower part. Concluding, we have analyzed the in-plane short beam bending behavior of these hybrid structures. We have compared the two different materials for the skin, aramid composite and carbon composite. We have found a similar mechanical behavior. There were just a difference in the residual load capacity that is probably due to the different damage mechanisms that have been observed. Thank you for your attention.
Thank you for your talk. Any questions or comments? I have a curiosity. Did you observe at the top of the skin on the core? Okay. Okay. Grazie soltanto. Thank you again.
Thank you.
The next lecture is entitled Numerical Analysis of the Influence of the Contact Boundary Condition and Specimen Geometry on Concrete Compressive Strength, and it is presented by Leandro Frederick. Leandro?
Hi, Sabrina.
Hi.
I see my screen.
Yes.
Okay, thank you. So, good afternoon, everyone. I'm Leandro Friedrich, and I'm going to present our work named Numerical Analysis of the Influence of the Contact Boundary Condition and Specimen Geometry on Concrete Compressive Strength. First of all, I would like to say thanks for the co-authors from Federal University of Rio Grande do Sul, Brazil, and the University of Parma, Italy. This presentation is divided as follows. First, a brief introduction is presented, and after that, the lattice discrete element method formulation, the model description, the results, and finally the conclusions. First, are you seeing my screen, Sabrina, just to check, because it seems not...
Just a moment, Leandro, because we have a problem.
Okay, no problem.
Because the presentation is fixed on the first slide and doesn't move.
Okay, let me try another thing just here.
Io comunque non sento niente.
Now is okay?
Yes. Please, Leandro.
Yes?
Perfect, perfect.
Okay, thank you. So this presentation is divided as follows. First, a brief introduction. After that, the lattice discrete element method formulation. So I'm going to present the model description, the results, and finally the conclusions. So axial compressor testing on concrete allows to measure the material compressive strain, being this mechanical property fundamental to define its field of application. However, in this type of testing, many parameters can affect the compressive strain value, leading to an erroneous estimation. The experimental investigation of such an influence is expensive and time-consuming, and in such a context, numerical simulation can represent an alternative to integrate the experimental data. In the present work, so numerical simulations are performed by using a version of the lattice discrete element method, named LDIN, implemented on the Abacus software. The influence of the contact boundary condition between the sample and the testing machine, the slenderness levels, and the cross-section shape that is circular or square on the compressive strain are here numerically investigated. So the lattice discrete element method consists of a set of masses joined by bar elements characterized by a regular cubic arrangement. The bars are characterized by a bilinear constitutive law, which allows to take into account the irreversible effects of crack nucleation and the propagation. Here in the figure below, it's possible to see the cubic arrangement used in the simulations and also the bilinear constitutive law applied to simulate the fracture in the lattice discrete element method formulation. A random field is introduced for the fracture energy, GF. So this parameter is modeled by a Weibull probability distribution, and it's assumed that the material fracture energy may be appropriately modeled as a random field characterized by a bilinear space correlation, defined by 3 correlation lengths in the coordinate directions. The proposed methodology can be used to represent so the heterogeneities of the material, like, for example, the aggregates in concrete. In the figure below, it's possible to see the bilinear constitutive law, the original bilinear constitutive law, the random field of the fracture energy, and associated with each bilinear constitutive law of different constitutive laws employed in the model. The LDIN is introduced in the Abacus explicit environment in order to create hybrid models between the lattice discrete element method and the finite element method, where it's possible to use each model's advantages and the potential. More details about this combination is available in the work of Schumacher. So, about the model description. 2 models are used to simulate the decompression test. Model A, where just discrete elements are used, and model B, where a hybrid model is used with the concrete simulate with discrete elements, and the steel plates simulate using finite elements. 2 boundary conditions are used for each model, frictionless and fixed. Here in the figures, we have an example of the model A, where such a boundary conditions are applied directly to the nodes of the discrete elements. And here an example of the model B, where the boundary conditions are applied in the interface between discrete elements and finite elements using cohesive laws presented in the software Abacus. For model A and model B, the following slenderness levels are considered with the parameter B of the cross-section of the samples equal to 100 millimeters in all cases. And for the slenderness level equal to 2, a circular cross-section is also examined considering the boundary conditions applied in model A and model B, that is, using just discrete elements using a hybrid model. About the results, so the figure shows the axial compressive strength in the vertical axis and the slenderness levels analyzed in the horizontal axis for model A and the model B, with black and red colors respectively. So about the results, we can observe that model A and the model B have similar trends. For the frictionless boundary condition, the slenderness does not influence the results, as it's possible to see here with the solid red and the black lines. However, for the fixed boundary condition, the slenderness has a significant influence, and we can observe here in the dashed the black and the red lines, the maximum difference obtained is equal to about 250% for both models when we use the fixed boundary conditions and the different levels of slenderness. When we analyze here the influence of the cross-section shape, here the figure we have the axial compressive strength in the vertical axis, and in the horizontal axis we have the different models, model A and the model B, and also the different cross-section shapes. So about the figure, it's possible to observe the cross-section shape influence the compressive strength independently of the model applied, that is model A on the model B. And for the frictionless boundary condition, the average distance, the average difference between the models is equal to about 260%, whereas for the fixed boundary condition, such a value is equal to about 265%. So about these results, we also analyzed the rupture configuration. Here, just the model A and the model B, just for the frictionless boundary condition is shown, and also experimental evidence obtained from Bandeira, where the authors use Teflon to decrease the friction between the samples and the testing machine. As we can comparing the rupture configuration, it's possible to see a kind of agreement between the numerical results and the experimental ones. So concluding, from the results presented, it's possible to conclude that the contact boundary condition and specimen slenderness influence the compressive strength. The cross-section shape also influences the compressive strength, and the discrete element approach can be a good tool to analyze the damage in the final rupture configuration. In the future works, we expect to apply also the extended finite element to compare the results with those here presented and also with our experimental campaign. Thank you.
Thank you, Leandro, for your talk. Any questions or comments? Okay.
I have just a curiosity. I'm going to ask you if you performed any comparison with experimental data.
At the moment, not, because it will be the next step of this work when we will perform our experimental campaign and calibrated the material behavior numerical with the experimental and the rupture configurations too.
Thank you.
Thank you again,
Welcome.
Leandro.
Okay,
the
thank you.
next lecture is entitled Bond Slip Behaviors between BFRP bar and ecological high ductility concrete using the beam test, and is presented by Liwan Chai.
Okay, Professor, can you hear me?
Yes.
Okay. Thank you
And
very
I
much
can
for
see your screen. Okay.
Okay. Thank you. Thank you very much for Chairman, Professor Sabrina. Professor Sabrina is my co-supervisor when I study in University of Parma. Thank you. Good afternoon, everyone. My name is Lijian Chai. I come from Taiwan University of Technology, China. Professor Li Pingguo is my PhD supervisor from Southeast University. Today, my topic is bond slip behaviors between BFRP bar and ecological high ductility concrete using the beam test. My report contains 4 parts. First, I will give a brief introduction. Second, I will present the experimental program, then the bond sleep behaviors, and last I will give a brief conclusions. In the bridge engineering, there is a difference of elastic modulus between expansion joint and the concrete transition zone, resulting in an inconsistent deformation of the two kinds of materials. Thus, the expansion joint damages. Ecological high ductility concrete has an ultimate tensile strength of more than 0.5%. We usually use the ECO HDC for the abbreviation. We can use ECO HDC material to cast the bridge deck link slab, replace the traditional expansion joint. Usually, we set the FRP bar as the reinforcing bar. This is a picture show the bridge deck link slab. The link slab is in the negative moment zone and by the flexural tensile deformation. The bond behavior of BFRP bar embedded in ECO HDC can provide the embedment lag for the link slab. So beam test is connected to analyze the bond slip property between ECO HDC and BFRP bar in this study. This is a picture for the test setup. The beam specimen contains two half beams, and BFRP bar is set in the flexural tensile zone. LVDT, this is LVDT. LVDT is set to monitor the slip of BFRP bar. In this research, we consider three factors: diameter, embedment lag, embedment set as 3 diameter, 5 diameter, 7 diameter. Then we also consider the cover thickness. Then we go to the bond slip behaviors. The filaments are related to the embedment lag, diameter, and cover thickness. When the embedment lag and diameter are smaller, the cover thickness is sufficient, so the filament is BFRP bar pulled out with specimen intact. For the BFRP bar diameter of 8 mm, when the embedment lag is less than 5 diameter, then the filament is BFRP bar pulled out with specimen splitting along the bar direction. When the embedment lag and the diameter are larger and the cover thickness is insufficient, the filament is BFRP bar pulled out with specimen splitting along two directions, this direction and this direction. And then we also analyze the bond stress slip relationship. We consider the embedment lag cover thickness effect. All bond response curves contain 4 stages. At first, we see the linear stage, then go to the non-linear stage. After the peak, the descending stage occurs and the residual stage. This is residual. This is also a residual stage. We analyze the effect of BFRP bar diameter on the feature values, such as the embedment lag, cover thickness. From the picture, we can see as the diameter and of BFRP bar increases, the peak pour out load increases for this picture and for this picture. It's an increase. While the bond strength decrease, this is a decrease trend. We also consider the embedment lag effect. As the embedment lag increases, the peak pour out load and free and slip increase. As this picture and this picture, it shows an increase trend, while the bond strength decreases. For the cover thickness effect, we can see as the cover thickness increases, the peak pour out load and the bond strength and free and slip increases. Then based on the analysis before, we proposed the embedment like the two equations here. This is two equations involve the size of BRP bar as the diameter and the tensile strength of BRP bar and ECOHDC material. The slip coefficient, cover thickness coefficient, and the installation positive coefficient is constant. Based on the two equations, we choose the larger embedment like as the desired value. And last, I will give a brief in conclusions. First, we consider the filaments. Filaments are related to the embedment like diameter and cover thickness. As the diameter increases, the peak pour-out load of specimen increases, while both bond strength decrease. As the embedment like increases, the peak pour-out load and free end slip increase, while the bond strength decreases. As the cover thickness of bar increases, the peak pour-out load and bond strength, free end of slip of specimen also show an increasing trend. And last, we give the embedded like BRP bar value when desire the bridge tackling slab. Okay, my report is over time limit. If someone has interest with my direction, please contact me through the it's in my email address. Thank you for your kind attention. Thank you very much.
Thank you for your report. Any questions Any questions or comments?
No. Well, I have a question. Why did you use the paper that
Okay. In my study, the bond behavior of BRP bar embedded in ECOHDC is studied to provide the embedment like in the bridge tackling slab. The link slab is a kind of flexural member, so the beam test is used, and the direct pull-out method doesn't reflect the actual state in the flexural member. Okay, thank you, Professor. Thank you.
Thank you. Thank you again. The next lecture is entitled Experimental Characterization of the Ultimate Angle of Ultracute GFRE Structural Elements, and is presented by Alessandro Fascetti. Alessandro?
My student Hadi will present this. Thank you for the introduction. So Hadi, Hadi, please go ahead.
The name of your students is
Hadi Habazadeh. So he's right here in the room.
Yeah, I'm going to present.
Okay, perfect. Now I can see you. Yeah. I can see your screen. Okay, perfect. You can start.
Yeah, hi. I'm just working with Dr. Fascetti, and I'm going to present this work now today here. Here today we are going to talk about an experimental investigation on the fracture properties of the GFRP elements. For the outline of the content, I'm going to talk about the introduction and motivation, then experimental characterization and data analysis, and finally conclusion. For introduction, in the last decade, fiber-reinforced polymeric structural elements emerged as an attractive and economically viable alternative to traditional materials in the construction industry. And this is mostly due to recent advancements in the field of materials science, with the new solutions being developed for both the polymeric matrices and the embedded fibers. Pultrusion is an efficient and economically viable continuous production process that produces structural elements with uniaxial fiber bundles. Here on the right side, you can see the figures for the structure of these elements. and how the fibers and epoxy get together with some process which called pultrusion to produce our different sections that we can use in civil engineering applications, and also these structures. Here, there are some examples for both building and infrastructure that engineers use this material, and nowadays they become more famous in the engineering society to use this material instead of, for example, steel. The experimental evidence shows that the transversely orthotropic behavior of the material and the relatively low strength and stiffness in the direction orthogonal to the fibers can cause a premature failure in pultruded composite structures. Here we can see two figures show some experimental study by Bank at 1994, and we can see the major problem here with the I-beam pultruded FRP elements, which is the web flange failure in web flange junction. As you see here, this is the major problem because of the lack of fiber in the these two zones showed in the in this figure. The web flange junctions can exhibit lower fiber content, as I said, as a result of the pultrusion process. This is the problem of processing in the pultrusion, and accurate predictions of the ultimate strengths of such areas are of crucial importance in the evaluation of structural behavior of structural assemblies. Here in the experimental work, the coupon sample were obtained from a pultruded GFRP structural halo section by means of a CNC machine, and three fiber direction were selected: 0, 45, and 90 degrees, the fiber load orientation degree, I mean, for the both tensile and 3-point bending. Figures shows us all our samples for tensile and bending tests. This is the figure which shows how we cut our samples from the main pultruded GFRP halo section provided for us by a CNC machine, and the figure B and C shows us the dimension. We selected both same length of 160 millimeter, and the spatial the rectangular shape for the bending, and this coupon test for the tensile coupon test shape for tensile test. For all of the samples, the thickness was 7 millimeter. The experimental test was completed, and after failure, we have this figure of the 0 degree, 45 degree, and 90 degrees. As you see, because in the 0 degree, there is 100% of fiber inclusion in the test. We have the failure in the weak fibers. Because of that, there's not such rupture in the whole specimens. But for 45 degrees, the crack path shows us the 45 degree, and for 90 degree we can see that almost there's no fiber effect and almost matrices effect here. Again, same process implemented for the 3-point bendings. Here, in the 3-point bending, we can see the 0 degree crack path line, and 45 degree and 90 degree Again, almost same scenario happened for the 3-point bending test. If you want to see the result as the analysis, we have the stress strain behavior of all test types. The significant scatter is observed during the test, and the 90-degree orientation shows us the highest value of standard deviation and coefficient of variation. Here we can see that because of the fiber effect, we can see that the 0-degree is almost 10 times greater than the 45-degree and approximately 20 times greater than 90 degrees. Again, the stress strain behavior for the 3-point bending shows us the almost a brittle behavior in our samples, and again, significant scatter is observed during the test, and 90-degree orientation shows us the highest value of standard deviation and coefficient of variation. Here, the 0-degree shows almost 5 times greater stress than 45 degrees and almost 10 times greater than 90 degrees fiber to load orientation. And in this figure, we have the normalized stress and normalized strain data for all types of tests with different fiber, for 2 types of tests with different fiber to load orientations. And as a conclusion, the pulverized GFRP materials, we know that are novel materials that can be employed in a wide range of the structural applications. Experimental study demonstrated significant scatter in ultimate strength as a function of load to fiber orientation. And the relatively high coefficient of variation obtained experimentally suggests that the ultimate resistance of GFRP element is highly dependent on the local density and volume ratios. Finally, ongoing research will aim at quantifying the influence of local strength and stiffness on the ultimate microscopic strength by means of stochastic numerical modeling approach. Thank you for your attention, and you can contact me by this email.
Okay. Any questions or comments? Any questions or comments?
Well, I have just a curiosity. If you can go back to slide 9, which is the mode of fracture for the specimen on the left-hand side. That is one with 0
this
degrees.
One?
Yes.
Yeah. Sorry, again, please.
Yes, which is the mode of fracture for the specimen with 0 degrees?
The rupture happened again same as 45 degrees and 90 degrees. It was mode 1 it was mode 1.
Oh, okay, thank you.
You're welcome.
Structural health monitoring of composite structures by means of and it's done by Boyang. Boyang, I can see Boyang. I cannot see Boyang between the participants. So the lecture. The next lecture is entitled Combined Effect of High Strain Rate, Elevated Temperature, and Triaxiality on Commercial Tungsten Alloy, and is presented by Ezio Cadoni.
Hello.
Perfect. It's okay, perfect. I can see your screen. You can
Okay,
start.
perfect. Thank you. So the aim of this contribution is the description of the mechanical characterization of a commercial tungsten alloy under extreme conditions of temperature, loading, and triaxiality. In fact, these aspects are crucial, and many industrial applications have to consider them. For this reason, a deep knowledge of the mechanical behavior at high strain rates of considered material is required. In general, machinery manufacturing or transport, as well as energy industries, have important dynamic phenomena that are simultaneously affected by extended strain, high strain rate, damage and pressure, as well as elevated temperature gradients. These data were obtained at the Dynamat laboratory, the laboratory founded by me in 2006 in my university in Lugano. That is now one of the laboratories of national relevance recognized by the Swiss Confederation and Swiss National Science Foundation. Dynamat lab is specialized in the studies of dynamic response of material in a large range of strain rate, and it is well equipped with special cutting-edge technologies in this field. Tungsten alloy is a type of cemented carbide in which tungsten carbide particles with extreme hardness are embedded in a matrix metal such as cobalt or nickel. The carbide particles provide a hardness but are in themselves very brittle. However, combined with a ductile metal matrix, outstanding material properties are achieved. Such as high wear resistance, low friction, hardness at a high temperature. The most common application for tungsten alloy is the cutting tool for hardened steels, in which the hard carbide particles provide the cutting surface, and through the metal matrix isolate the particles from one to another and prevents the particle-to-particle crack propagation. There is a lack of experimental data on the thermomechanical response of these refractory metals to high strain rate effects at elevated temperature higher than 1000 Celsius degree. The behavior of material under these conditions is of a great interest from the phenomenological point of view. For example, testing the consistency of different constitutive models. Testing was conducted on smooth round specimen of 2 mm in diameter and 5 mm gauge length. 3 notches configuration were used to evaluate the effects of different triaxiality condition on stress strain, and keeping constant the net cross section of 2 mm in diameter. The quasi-static tests were carried out by means of an electromechanical universal machine, highlighting the elastoplastic and brittle behavior of this alloy. The dynamic response of this commercial tungsten alloy at high strain rate was investigated by using a split Hopkinson tensile bar installed in our laboratory, as shown in this slide. It consists of 2 straight circular bar with a diameter of 10 mm and the length of 9 and 6 meter. The first 6 meter of the longer bar is used as a pretensioned bar, while the rest 3 meter is used as input bar. The second bar serves as an output bar. The tungsten alloy specimen is screwed normally into the input and output bars. By means of a hydraulic jack placed at the end of the bar, and thanks to the blocking device, it's possible the pretension bar is pulled, so we can store elastic energy and regulate the velocity in relation to the load amplitude. So we have we obtain the signals, the very clean signals in terms of incident, reflect, and transmitted pulse, and the constancy of the incident pulse. The test we have carried out at a high strain rate at room temperature and elevated temperature, and the last one thanks to the induction heating system that we are able to heat up the sample to elevated temperature and obtaining the picture like this one. In this slide, I've resumed the results at a strain rate at room temperature on smooth samples. The strain rate effects on mechanical properties of this tungsten alloy can be observed in the table shown in the slide. By depicting the engineering stress versus engineering strain, it's possible to highlight the mechanical properties, and 3 targets of high strain rate were set as 850 strain per second and 422 strain per second, obtaining by imposing respectively at room temperature 26, 35, and 50 kilonewton in the preloading bar. In fact, it's possible to observe a significant increase of the strength and strain capacity. One of the main challenges in studying the influence of a high temperature on tungsten alloy under high strain rate is the lack of experimental data. And this is because it's very difficult to generate the necessary high strain rate loading in high elevated temperature. And this is why the preliminary study has been conducted. Keeping the same loading conditions, we have observed a general increase of the evaluated strain rate with increasing temperature. You can see the testing temperature use the same input signals. The input signals so is not affected by temperature, but the reflection waves are. With increasing temperature, the effective strain rate is expected to increase linearly. Now, at room temperature, with the constancy of 850 strain per second, we increase the temperature, and we obtain these results using the same preloading conditions, and the temperature varying from ambient temperature up to 1100 Celsius degree. And it can be noted that the strength of this commercial tungsten decrease with increasing temperature under strain rate loading conditions, and then fracture strain is increased in the same interval. The stress triaxiality at the center of the net section can be calculated by the formula proposed by Bridgman. And the material parameters of the Johnson-Cook damage model were obtained by using the experimental data. And according to this parameter, we have created the failure surface shown in this slide. On the right for 20 Celsius degree, and on the left for the 20 Celsius degree, 1100 for the right one. As a conclusions, this preliminary investigation on mechanical response of this commercial tungsten alloy was performed to analyze the effect at different temperatures and rated triaxiality. A methodology for testing materials at a high strain rate was presented. The methodology consists of performing dynamic test in tension using the split Hopkinson tensile bar, and heating the specimen using the induction coil system. The heating system is properly designed to concentrate the heat flux in the gauge length of the specimen, and the investigated range in the temperature was from temperature, for ambient temperature up to 1100. So the next step will be addressed to eliminate the problems of oxidation of these alloys, creating a vacuum protection and an improvement of the setup allows the fast video recording the test, creating the post failure phenomena. I'd like to thank our sponsor, Arma Suisse, and all of us for the kind attention. Thank you.
Thank you for your talk. Any questions or comments?
Did you perform a similar experimental campaign on other alloys?
Yes, usually we study a lot of materials, both for different industrial fields, for automotive, for nuclear, for defense, and so on. So this is we have a quite good experience in this field, and this is a particular because it's a very brittle material, and it is necessary for the manufacturing industry to know how the tools works in order to have a perfect works at the end of the process.
Okay, thank you again. The next lecture is entitled Influence of Stress State on damage, SEM in situ investigation and modeling, and is presented by Sara Ricci, correct?
Yes, good evening.
Good evening. Can you share your screen? Yes.
Yes, can you see it?
Yes, now perfect. Presentation mode, please. Perfect. You can start.
Good evening, everyone. My name is Sara Ricci. I am a PhD student at University of Cassino and Sate Lazio. Today, I'm presenting the results of an experimental investigation we carried out together with the Norwegian University of Science and Technology regarding the influence of the stress state on ductile damage. It is indeed well known that the stress state, the loading conditions have a strong influence of the fracture strain on the material, since different mechanisms can be activated and act together to cause the final failure of the material. One of the first parameters introduced to account for the influence of the loading conditions of material ductility was the stress triaxiality. And it's well known that increasing the stress triaxiality, materials exhibit a lower ductility, which is consistent with void growth model predictions. This is true under tensile dominated loadings, but in the presence of mixed or shear dominant conditions, different materials might exhibit different behaviors depending on their shear sensitivity. And these results highlighted that stress triaxiality alone is not enough to account for, to thoroughly describe the material behavior, and other parameters such as loader parameter, depending on the third invariant of the stress sensor, should be taken into account. In this work, we investigated the influence of the stress state on the fracture behavior of the aluminum alloy 2024, which is well known for its shear sensitive behavior, spanning from tension dominant to shear dominant loadings. And in order to do so, we optimized 4 different sample geometries, which realize different combinations of stress triaxiality and loader parameter. We also looked closely into the damage mechanisms in different steps of the loading process with in situ STM techniques. And we correlated the local strain to the experimental data with DSC analysis. And finally, we developed a material model, numerical model, which is able to represent our alloy behavior. As already said, we focused on the aluminum alloy 2024, which is a 2000 series aluminum alloy, so its major alloying element is copper. And as a result of the standard processing of the alloy, which includes solutioning, treatment, and quenching, followed by cold working, we have a very anisotropic grain structure with big grains elongated along the rolling direction. And during the last phase of natural aging, we have the precipitation of very large intermetallic particles. Here we can see the macroscopic load versus displacement response of our material for the different tested geometries. And as expected, the fracture surfaces exhibit a transition from tension dominant to shear dominant conditions. The sample with the 0-degree notch is indeed characterized by the presence of normal dimple, which are typical of tension-dominated loadings. The sample with a 90-degree notches is characterized by the presence of shear dimples that are developed under shear dominant conditions. For the sample with a 45 notch, we have instead both normal and shear dimples and a mixed mode of fracture. And looking closely into the fracture surfaces, they are characterized by the presence of very large broken intermetallic particles, which were found to be the major damage nucleation mechanism for this alloy. So what we did is that we monitored the behavior of these particles during different steps of the loading process, and we correlated the experimental results to the strain evolution in selected monitoring points evaluated with the DIC analysis. What we've seen is that these particles start to break very early during the loading process right after yielding. The particles that break first are those characterized by a bigger and more irregular shape because they have a higher stress intensification around them, and increasing the load, more particles start to eventually break. And what we wanted to do was to identify a nucleation strain that we defined as a strain at which most particles had broken, but damage had not propagated into the matrix yet. And increasing further the load, we can see that the newly created voids grow and eventually create microcracks that propagate into the matrix and cause the final failure of the material. These results are for the sample with a 0-degree notch. We found them to be consistent for the other tested geometries as well. We can see here the results for the 90-degree notched sample. What is different is the orientation of the fracture plane of the particles. They break in a very brittle manner, so their fracture plane is perpendicular indeed to the maximum principal stress direction. And we use these experimental results to evaluate a numerical model that to represent the behavior of this alloy under the different stress state conditions. First of all, regarding the plasticity behavior of the material, we decided to implement a Kronen-Falles cold yield surface. This is a yield surface. This yield surface is an extension of von Mises' criterion for shear-sensitive materials, and it takes into account both the second and the third invariant of the stress sensors. And depending on the parameters selected, we can have a behavior that is included between von Mises and Tresca yield surfaces. Regarding the damage modeling of the alloy instead, we implemented a plasticity damage self-consistent model, which is a damage model recently developed in the context of continuum damage mechanics. And it takes into account both the influence of stress triaxiality and of the third invariant of the stress sensor on damage. And moreover, the model is able to distinguish between different damage mechanisms such as void growth, sheeting, and west shearing. This model requires the identification of a nucleation strain law that we fitted on the experimental results we obtained from the SEM in situ testing plus the SE analysis. And moreover, we have to evaluate the failure locus of the material. And in order to do so, we evaluated the fracture strain for the different geometries we tested, and we also compared our material ductility to the data presented in literature, and we can see that our material has a similar response under tensile dominated loading conditions, but compared to other experimental results, it's shown a higher resistance under shear conditions. Here we can see the prediction of the material response with the numerical model we developed. We can see that the model is able to represent with a high level of accuracy both the hardening of the material and the strain evolution for the different tested geometries. And we can also predict very well the fracture behavior of the material. We can see here, in fact, that we can represent the fracture morphology under shear dominated loading conditions. For the 90-degree oriented sample, we have a slanted fracture, while we have a change in the path crack propagation for the 45-degree oriented sample. So in this work, we investigated the fracture response of the aluminum alloy 2024, which is an alloy used in the aeronautical field, and it's known for its shear sensitivity. We also investigated damage mechanisms and their evolution during the loading process in order to identify a nucleation law for the material. And finally, based on the experimental results, we evaluated and developed a numerical model which is able to represent our material behavior. Thank you.
Thank you for your talk. Any questions or comments?
Well, I have a question. Can the proposed procedure be applied to a real component?
Yes, we actually, not for this material, but we use this same procedure and the same model also for AM materials in order to evaluate the behavior under real impact conditions.
Okay,
thank you. The next lecture is entitled on the gauge. The next lecture is entitled the gauge test and by correct?
Yes, but I'm still Ezio Cadoni, and I substitute.
Sorry. Okay.
Okay. Now from the industrial application now to the civil engineering applications and technical methods. The design of a structure that can withstand the dynamic loads requires a deep understanding of the dynamic behavior of materials. And natural events such as a hurricane, earthquakes, rockfall, or tsunami, or human accident actions such as impact or blast can trigger this type of actions. The Kolsky bar or split open zone bar is universally recognized as the most appropriate method to study material behavior in the strain rate range of 100 up to 1,000 strain per second. The dynamic equilibrium is an essential requirement that has to be met in order to ensure a uniform state of stress and strain across the specimen. 3 around trips in the specimen are generally accepted as the necessary amount of time to reach this state. And therefore, the shorter the sample, the earlier equilibrium will be reached. Specimen gauge length is then a critical factor affecting both plastic strain rate and deformation capacity. The project I'm presenting is an experimental. Yes, I'm moving.
Now it's moving. Sorry.
The project I'm presenting is an experimental and numerical investigation addressed to this issue in the laboratory that I presented to speech before. And the tensile testing at a high strain rate was performed by means the split open zone tensile bar installed in our laboratory. Pulling the pretensional bar that is clamped in one hand and by blocking device, and the other is connected with an hydraulic actuator, it is possible to store elastic energy in it. The preloading governs the test velocity. The test starts by releasing with the brittle fracture of the bolts in the blocking device, so that the incident wave pulse propagates through the input bar, reach the spaceman, and at that point, some part is reflected back and another is transmitted to the output bar. The pulse were recorded by means of string gauges in the two bars, and the graph shows the input and output signals as a function of time. We have used commercially available P500A steel rebar, the round samples having 3 millimeter in diameter with 3 different gauge lengths, 5, 10, and 15 were used. The specimen were obtained by a 12 millimeter rebar. The common belief for that long specimen in general are not adequate for split Hopkinson tensile bar is now discussed. This issue is related to the stress equilibrium, the stress uniformity, and strain localization. The question is, what is the optimal gauge length for dynamic tensile specimen? Or is it true that longer specimen is not adequate, and why? Let's consider the stress equilibrium. In this slide, I've reported the signal obtained for 5 and 15 gauge length. You can see that the equilibrium is reached in the elastic part of the material response. And this is evident observing that incident and reflected pulse signals, incident plus reflected signals are equal to the transmitted one. Reported here, the load versus time curves for the 2 gauge length shown before, considering the stress, strain, and strain rate formula, it is justified the application of a simplified and well-known explanation of the split Hopkinson bar theory, that is this one. By imposing the same preloading to the pretensional bar, different material response are recorded because of the gauge length. So different strain rate are imposed, consequently change strength and strain capacity. To solve this problem, the pretension must be increased by increasing the gauge length. As a result, for the same strain rate is obtained as well as the response described in terms of stress time and stress strain curves, and obviously the two curves are identical but differ only after the making phenomenon. Regarding the deformation state, in the specimen with 5 millimeter and 10 millimeter gauge length, the neck developed in the middle, and the neck for the longer gauge length, the neck developed near the end at 20–30% of the gauge length, as found also by other researchers. The specimen profile has been measured, and before and after the test is shown in the slide. And this graph refers for the case of 5 millimeter and 15 millimeter. On the base of this measurement, the plastic strain is derived from the natural logarithmic of the ratio between initial and final cross-section, and 2 observations can be done. First, the dimension of the necking zone is constant, as well as the failure plastic strain. The second observation is that in the longer space sample, The plastic strain shows variations that indicate possible plastic localization in the pre-necking phase. So a numerical simulation of dynamic tensile test was conducted using LS-DYNA to analyze both the distribution and the evolution of the plastic strain, as well as the dynamic neck formation. The specimen was modeled using our model, the DAMP model, which take yielding into account as a transient propagation of the shear waves from the initialization point. For this preliminary simulation, 8-node hexahedral solid element were used, and a mesh size of 0.46 millimeter was used for the specimen and 0.92 millimeter for the bars. In the case of the long specimen, the mesh size allows for the highlighting the deformation phase during the transition from elastic to plastic, the uniform deformation and multiple plastic localization in the initial phase, and plastic deformation as shown in the slide. And the necking at high strain localization is experimentally and numerically analyzed. So in the next two slides, we will see this is the experimental results, so the picture of the broken specimen, different with different gauge length, and this is the simulation obtaining a very good similarity. To conclude, the use of short specimen is recommended, but not mandatory, provided adequate numerical calculations are carried out along with the experiment. Samples with 5, 10, and 15 millimeter gauge length were tested and modeled in order to validate the uniformity of the stress and strain, the gauge length during the experiment in the pre-necking phase, in order to obtain the same plastic strain rate using different gauge length. In the split Hopkinson bar, the preload have to be adapted. The use of longer samples still allow to obtain a uniform state of stress and strain. The short specimen fail and the mid-length due to the parabolic strain distribution, whereas longer specimen can fail anywhere along the gauge length due to their uniform strain distribution. The use of a shorter sample guarantees that the neck develop in the middle, assuring, for example, to concentrate the analysis, the attention, the video and so on, and the other measuring tools in the known position. Thank you for your attention.
Thank you for your talk. I'm sorry, but we haven't time for comments or questions, and we have to move to the next lecture. Thank you again.
Thank you.
The next lecture is entitled Prediction of Chlorinated polyvinyl chloride, CPVC POPs residual life under the effect of a defect, and it's presented by Fatima Gugouch. Fatima?
Yes.
Hey, I can. Yes.
Hi.
Can you,
good evening.
yes.
Everyone.
Can you move to the presentation mode? Perfect. You can start.
Thank you very much. First of all, I would like to thank the Committee of Organization, the Monitor. I am grateful to present a part of my work titled Prediction of Chlorinated Polyvinyl Chloride, the CPVC, by residual life under the effect of a defect. For this presentation, I will commence with introduction, then experimental procedure and operating mode, after analysis of experimental results, and I will finish with conclusion. Plastic are ubiquitous in almost all sectors.
Sorry, but we lost the speaker. A moment. A problem with the speaker that she isn't okay. Fatima, you have to open your microphone because I can't hear you. Okay, we can move to the next presentation. And call Fatima again at the end of the session. Fatima, I'm moving to the next presentation. Solve your problem, and I will call you again to the last. Okay.
Okay. I continue or do you hear me?
Connection is now stable. If you want to, did you solve your problem?
Now you can see my screen?
Yes, continue, please.
Yeah, thank you. I'm so sorry. It's a connection problem. Now from this. Hello? Could you hear me? Yeah. From this figure, from this two figure, we notice that the plastic is very important due to their very low price compared to the copper and other performance such as insulation technical resistance to corrosion. And from a mechanical point of view, the use of polymer lies in their failure associated to various degradation, which affect the CPVC structures such as mechanical fatigue, etc. That lies to reduction of resistance capacity of piping network, and finally breakup and failure of structures. The objectives of this study is to study the mechanical behavior and then predict the lifetime of CPVC structures based only on static test without recurring to restoring to dynamical test highly and don't demand in high times. It's scientifically characterization of mechanism of damage, and industrially it's answering human safety, protecting environment, and avoiding materials losses. Now we see the experimental. Before starting birth test, we prepared specimen. A 3 specimen, virgin specimen cutting from the CPVC tips to characterize the material, and then we prepared 21 notched specimen with a defect form of half ellipse with different depth. Then we move to the experimental apparatus where we fix the end of cuff for every specimen. Then we connect the specimen with the hydraulic pump and immersing it in the bank to avoid the accident. And the specimen is exposed to a continuous pressure until failure. Based on the results, it's the evolution of pressure according to the time for the undamaged pipe. And this figure shows the evolution of the internal pressure as a function of time for the defected pipe at different depth. And we show that the property mechanic includes with the increasing of the depth. This illustration shows the drop of the pressure as a function of fraction of life that's equal the depth of the defect per thickness of the pipe. And this figure shows the two modes of fracture for the specimen with a small notch. It's ductile for a fracture, but for the specimen with a large notch, it's a brittle fracture. Based on the results and by using the static damage model based on ultimate stress pressure, we draw the evolution of the static damage as a function of fraction of life, and then this is the model with the PRC, the residual ultimate pressure of knotted specimen, and the PU, the ultimate pressure of a virgin specimen, and then we determine the three stages of the evolution of the damage. First stage corresponding to the initiation of the damage. The second stage, it's very important, especially for the industrial. In that stage, the predictive maintenance is required. And the last stage, and third, where the brick is brittle and it's necessary to change the structures. Based on the static test result and with increasing in the notch depth, we notice a drop in mechanical property and increase of damage. Based on the pressure method, then we determined the different stage of damage and also the mechanical behavior of CPVC structure. In this case, we were interested by the piping. Thank you for your attention.
Thank you for your talk. Any questions or comments?
I don't hear you very. Yes.
Only thank you for your talk. Any questions?
No, I hear you. No, I hear you clearly.
Okay.
Yeah.
There is a question. Thanks for your presentation. I would like to ask you whether you will try to model this failure also in fracture mechanics terms and not with the damage approach.
Yeah. When?
It's more a curiosity whether you will try to use a fracture mechanics approach to model your test
result. To accelerate the damage behavior, and after that we based on the result, we can predict the lifetime of the structure, and the second stage. It's very important that we can play maintenance predictive, but the last stage, it's in this stage we have to change the structure to avoid the accident.
Okay.
Predict.
Okay. Thank you again. The next lecture is entitled Designing the Staple Connectors of the Parthenon's West Tympanon, and it's presented by Antigone Brova. Correct? Can you open your microphone, please? Antigone, you have to open.
Yes, thank you. Thank you very much.
Yes, and move in presentation mode.
Okay, thank you very much. And good evening. This presentation discusses the redesign of the special connectors of the Parthenon's pediment. The pediment or tympanon is the triangular part of the facade between the horizontal here and the raking cornice of the temple. In that part, the sculptures were situated. Here a drawing depicting the west pediment of the Parthenon as was preserved in 1674. In the case of the Parthenon, the pediment consists of two parts. The first part, which the background for the sculptures, is formed within marble slabs called orthostates, and the second part is constructed as a simple massive isodomic wall with marble ashlar blocks, which is called backing wall. In the initial construction, several connections were provided to unite the two individual parts of the tympanon along with the cornices. As can be seen here in a schematic drawing of those connections, metal dowels were used in vertical direction for joining the blocks of the tympanon with a horizontal cornice in purple and with the raking cornice in orange. And also metal clamps were used for joining adjacent individual blocks together in the horizontal direction, both longitudinally, here in blue, and transversally here in green and red. Especially these transversal connections are essential as the backing wall acts as a counterweight to the orthostates that have a natural tendency to overturn during seismic excitations. The so-called twisted connectors were a special feature in the original structure. Here are presented in red. In the current restoration project, where the central part of the west pediment of the Parthenon is being restored, the need for the redesign of those connections arose. The redesign had to account for the damages of the monument and meet the standards of safety, especially during earthquakes. The orthostates suffered fractures in the anchorage area of the dowels and the connectors relative to their actions, along with damages caused by the bombardment of the monument during the Turco-Venetian War, and vertical cracking of the blocks relative to the crystallic structure of the marble. Those blocks were all dismantled and restored before being put back to their original position. The most severe damage, though, is that of the backing wall, provoked by the 2nd century AD fire, caused severe cracking to the inner part of the isodomic wall. As can be seen here, though the facade of the block seems intact, a multi-fractured texture exists in depth for about half of the block's width. The mechanical properties of the stone are severely compromised, and so is its bearing capacity. It should be noted that this was the actual condition in the anchorage position of the transversal clamps before the restoration works. The blocks are, to the extent it was possible, restored. In order to assess the seismic risk and the forces that would be induced to the connectors, the construction was modeled using DEM analysis, and the models of the structure were calibrated using real accelerograms obtained by an installed accelerometric array in collaboration with the Geodynamic Institute of the National Observatory of Athens, along with the Acropolis Restoration Service. The calibration procedure consisted of using as input the base registration and comparing the output on the top of the columns with its respective registration. The parameters of the models were thus defined. The calibrated model was then used to establish the design forces acting on the connectors between the two parts of the tympanon, meaning the orthostates and the backing wall. The seismic events selected were chosen to correspond to the worst-case earthquake that could have occurred in Athens in more than 2,000 years, and various dimensioning schemes for the connections were evaluated. The connections proved numerically to be crucial for the behavior of the tympanon and the avoidance of a possible collapse of the central orthostates towards the west. Here, the numerical analysis results are presented for 4 selected seismic events that were evaluated and proved crucial in the case of the freestanding orthostate, meaning without connections between orthostate and backing wall. Significant damages with collapses of the orthostate blocks are predicted by the numerical analysis, thus pointing out the significance of the connector's redesign. The analysis provided the design forces for the connections. It had been decided that the connections would follow the ancient arrangement, meaning the connectors had to be anchored in the ancient sockets provided by the original structure. The initial design aimed not only to carry the design loads, but also to maintain as much archaeological evidence of the structure intact, with the additional pursuit that the system remained hidden in the core of the marble blocks, similar to the original construction, at least for the west facade of the orthostate. For the backing wall, it was already decided, due to the heavily damaged core of the blocks, that the connectors should be anchored to the east facade here to ensure the counteraction of the wall. The connection that was designed contained 2 titanium parts connected with a special nut. Here. The part anchored to the orthostate was an L-shaped rod inserted in a drill hole inside the orthostate. That part was smooth and was secured in place by very good fitting without any mortar in order not to disturb the ancient sockets, and threaded at the other end for the nut to engage. The part that penetrated and was anchored to the backing wall was a simple rod threaded for the nut to engage, and while the other end had the form of a cut-off cone in order to meet the requirements of the least damage to the hosting ancient socket, resembling a barrel anchorage with wedges. In situ testing of the anchorage scheme of the special connectors was performed in order to test their capacity. Here are the 2 types of the L-shaped rod to be inserted in the orthostate blocks with different anchorage lengths that were tested. And here are the specimens for the simple rod with the barrel anchorage. Image from the specimens ready for testing. These are the specimens to test the capacity of the part anchored to the blocks of the orthostates, and these are the specimens to test the capacity of the part anchored to the blocks of the backing wall. The tests were carried out in the working site of the Parthenon with the help loading device and measurement instruments from the National Technical University of Athens, and more specifically the Laboratory for Earthquake Engineering. The tests showed that the anchorage of the backing wall was sufficient to carry the design loads of about 7 tons, while the L-shaped roads proved unable to reach the desirable load limit set for the design and slipped out of their hole at a lower pull-out force of about 2 tons. The design of the connections was re-evaluated then, and anchorage to the orthostates was considered with securing the L-shaped rods with cement mortars. Thus, the part inserted to the marble was threaded. 2 types of threading were considered, typical and low, to avoid unnecessary large drilling to the marbles. And the specimens after their assembly were left for the cement mortar to cure in order to be tested. 3 of the anchored L-shaped rods were tested until their failure. The results of their loading capacity were in the required design level with a minimum capacity of approximately 9 tons. It was then decided to model the composite anchor system with both the parts connected with a special nut tested simultaneously. Thus, 5 specimens were designed to be tested, assuring that the anchored part in the orthostate would not fail before the horizontal one that would be inserted in the backing wall. The horizontal part was inserted in the loading hydraulic jack, and the results showed that the anchorage system can be trusted, since only the intended part was systematically failing within the desired design loads, reaching an ultimate force of about 8.5 tons. After describing the exact damage the drilling will cause to the ancient sockets, both in the orthostate blocks and the backing wall blocks, the design was finalized. Thank you very much for your attention.
Thank you for your talk. We haven't time for a question or comments, and we have to move to the, thank you again, and we have to move to the next lecture. The next lecture is entitled Experimental and Numerical Analysis of the Effect of Strips on Concrete Tensile Strength, and is presented by Louise Kostesky.
Hi, Sabrina. Hi, Andrea.
Hi.
Hello. Well,
Perfect.
yes, it's okay.
Present. Perfect. Now, yes.
Perfect. Well,
you can start.
Thank you very much. Good afternoon, everybody. I will present this work. This is a very basic work. What we do in this work? We are studying the splitting tensile test. How change the result of the splitting tensile test when we use different strips of metal or wood. Well, for the experimental study, we use a concrete with a characteristic strength of 45 MPa. This is the material properties, and in this figure is the size of the material, and here is where we do the samples. We use 10 samples for each configuration, and there were we use cylinders by 100 millimeter diameter and 200 millimeter height. This is the common usage in Brazil for the industry. Then we use this size of the specimens for our study. We do all the study at 28 days. Well, here I show the compressive test only for check the material properties, and then I will present the result of the splitting test with four different strips. The first one is the wood strips, that they are the standard one, and the others are with steel strips. This steel strip have a curvature equal to the specimen. Then with different sizes, 10 millimeters, 15 and 20 millimeters. Well, for do the numerical simulations, we use the lattice discrete element method. This method consists on of use a lattice, see, a 3D lattice to model the solid. Then we have a special discretization of the solid by a 3D lattice. All the properties of this lattice are related to the characteristic of the solid. And the time discretization is used, the equilibrium formula very well known, and where M is the mass matrix, C is the damping matrix, F and the internal force and the external applied, and we use the system of integration, explicit finite different scheme to integrate this equation. Okay, well, all the properties of the elements of the modulus of the LDEM are related with the fracture energy of the material in the constitutive law. The area of this constitutive law is related with the fracture of the material. Then this parameter, this other parameter is the critical deformation is related with the maximum force that this bar can have. Well, we use this this method in the abacus explicit. We put this using a law that is available in the abacus. This is one, and all the lattice is modeled by a 3D truth finite element, T3D2 element. And then we put all the system, all our simulations in the abacus and do in the abacus these simulations. They have more facilities. Also, we have random properties of the. We can represent the random properties of the material. How we do that? Every element has a different constitutive law. The constitutive law of the elements are related with a Weibull distribution like this. Then all the material has a random properties like this. This is very utilized when you simulate concrete or some or one other almost brittle material. Sorry. Well, this here is the representation of the random distributions of the properties in a cylinder and the view of them. We use a mean of fracture mechanics in this case for 146 Newton by meters, and the correlation length of 40 millimeters, and a variation, yes, of 40% of the fracture mechanics. These are the elastic modulus, and the other properties remain constant. Well, the result of the experimental analysis. The experimental analysis, we do 10 results for every one of these configurations, and we have the wooden strips resist 4.33 MPa, and the steel strips resist a little less, with 10 and 15 millimeters of size, and with the 20 millimeters of size is practically the same of the wood. Then we found that If you use the steel strips of 20 millimeters, the result is practically the same of the wooden material. This is the experimental result. We can see this here. The failure configuration is very similar when we change. The only difference is when we have steel strips for 20 millimeters, there appears some transversal fracture, more transversal fracture than in the other cases. Here appears someone, but in this case, almost always appears this transversal fracture that is not so common in this case. The numerical results, we do different models. Here is to model the concrete and the wood. And here we model the concrete, the wood, and the steel, the steel plate of the machine. And these three are the steel strips. And the results are different for the others, for the experimental. The behavior of the results of numerical result is different. Here we have for 4 MPa for wooden, and almost 6.5 for steel strips. Then the result is not so good. The final configurations are similar to the experimentals, but there is a little more, I don't know what to say, it's more linear. It's not so good, the results for the graphic configurations. When we do some 3D simulations, we can see that the cracks always start in the corners, not in the central part of the specimen, like say the theory. Then we start in the corner, and there in one corner the failure propagates to the rest of the rest of the specimen. Always we see the same problem. Well, conclusions. There is no difference on the resistance obtained between the wood strips and the 20 millimeter steel strips. This is an experimental conclusion. The failure configuration are similar, but in the steel strips appears these cross-sectional cracks. This is a problem. No, it's no problem, but this is. When we compare, are the experimental results with the simulations, the wood is very, very similar, the simulation of goods with the results, but the simulation of the steel strips are different and have a different behavior. We have here the experimental, and here the numerical, the behavior is different. When we compare the configurations, the results are okay, but we need to disturb a little more our configurations to have a more realistic ways. Okay, this is all. Thank you very much for your attention.
Thank you very much for your presentation. Unfortunately, there is no time for questions, so we will move to the next speaker. And the next speaker will present will be Jared Vincent Patoros, and will present road bridge, dappled, and girder analysis and preservation.
Hello.
You can share your screen. Yes.
Okay. Can everyone see my screen?
Yes.
Okay. Hi, my name is Jared Fataros. I'm with a consulting firm AECOM, and my work for the IGF27 is on dappled girder analysis and preservation. a state-of-the-art perspective on the problem and solutions. So first, the abstract is based on inspection, load rating, and rehabilitation of DAP-DEN concrete girders for in-service bridges. This discussion is based on analysis, instrumentation, and the validity of proof load testing, retrofit for the shear strengthening improvement, with a focus on the interface discontinuity between new and existing concrete. And this has basically been uplifted by field work done by my firm with bridge inspectors in the US, engineering analysis by peers here and abroad. And I just wanted to acknowledge US, Italian, and global researchers, academics, developers, inspectors, and engineers who have contributed to this body of work. Many papers from many different countries are looking at the same issue. But I'll start with the fundamentals and use the US code that has lots of ties to the Transportation Euro Code and other codes abroad. We all know a classic hundreds, if not thousands year old corbel condition, be it on Parthenon or on buildings, parking lots, or bridges. They can act as in-span hinges, inverted T's, but the common feature of this structural element is the nib point, where you have a reentrant and a stress concentration where your change of shear force is greatly increased by an either sudden increase or decrease of section. In this case, a decrease. The paper that was inspiring a lot of the conversation in the US on this was written by IGF, citation below left, and the Italian road bridges in the past, I think 8 years that have had issues with collapse. I believe 3 to 4 of them have had what we would call Gerber saddles, in-span hinges, or DAP-DENs. So what I'm showing is the Italian counterpart on my left to the US bridge state-owned here on my right that we're performing similar analyses and preservation for. From a fracture mechanics standpoint, we'll obviously start to focus in a little bit more on the analysis and the mechanisms of the steel and concrete, and that can't be done without strut and tie analysis. So here, the point is that the research right now on strut and tie models for this type of structure is very much dependent on the rebar detailing. As you can see on the right, depending on your rebar detailing, which varies much like a custom tool, it's really not done uniformly. And the analysis that engineers and researchers have to perform is laborious, detailed, and not necessarily simple. And we're here to talk about the simplicity of something that is complex and demystifying it and making it common knowledge so we know how to fix this problem. So these models follow a crack pattern that is observed in the field. As we look at field studies of crack patterns, codes prior to the 1969 era, we're not looking at each of these crack conditions shown on my left. And a lot of the under designs took place in the mid 60s, whereas the concrete code increased its understanding, which was again probably fueled by those in fracture mechanics and understanding multi-modes of failure and damage and how that propagates, along with the exposure of rebar that's obviously packly tight in these locations. So we'll touch on durability in a moment, but the key aspect of this point is both the analysis and the crack mapping come together in research now, where our field studies, instrumentation, and physical representation of the overstresses in concrete that is largely put in tension around that nib point where the rebar yields slightly. It becomes an entrance point for salt impregnation, for sulfides, and just for general durability concerns that then compound itself with the overstresses. So the crack is essentially an open wound. If you put salt in that open wound, that wound won't heal, even if you put a Band-Aid over it, which is getting to sort of an FRP point in a moment. So additionally, there's something in the code that I really want to bring up as well for this research community, is when you look at the horizontal forces on a corbel, most codes only require the design be checked for 20% of its total vertical load. And that is a huge exposure in the code, both here and abroad, because if we're not looking at site-specific lateral forces, what you're doing is essentially assuming a lateral force is enveloped and covered, but under design of bearings, as I show here, locking action will cause lateral forces in excess of the design code and can potentially have shearing consequences. Again, as this is a fracture mechanics forum, the brittle failure modes are typically seen on the structure type. And you can see here kind of the step one of that concern propagating at the bearing and a number 5 dowel that's been placed in there. So we also look at these field conditions from an instrumentation and proof load approach. Even within our firm, we have folks that look at the rehabilitation from an inspection standpoint, from an engineering analysis standpoint, but also from an instrumentation standpoint. And the instrumentation and proof load testing on these beams do sometimes show a greater shear capacity than our analyses show. So we're talking 10 to 20% greater, or sometimes more if they're, as you can see here, you have diaphragms that kind of add to the overall structural system redundancy. Some bridges have them, some bridges don't. And the non-standard nature of these, including the pre-stressing forces, which are present in some members and some have none. So, no two are exactly alike except for the common nib point and the diagonal tensions that are experienced at that point, which are our fracture and failure concerns in brittle modes. Again, a direct citation from the IGF last year brings up that major points of shear reinforcement in precast beams are not enough to ensure a category 3 bridge classification. So categorizing our bridges for either lateral or importance factors, if we don't understand that this element is complex, undercoding these bridge elements as something that looks simple, but actually contains lots of internal complexities and load paths is something that ultimately leads to a misunderstanding by lots of bridge owners. And by the time you have a bridge owner, that they need to understand how to maintain their home, so to speak, right? So repairs have been performed. We looked at repair recommendations such as fiber reinforced polymers and other wraps on the external and post tensioning, and all of these either had constraints due to the truck loading on top. You can't fit a bolt on top of the bridge deck like you can on, say, a parking lot or building. And also noting from the Italian example here that the bridge that was retrofit with FRP actually had a sudden failure was a direct correlation to the detail 2 shown on the bottom right here, where we considered it a limitation and constraint in our design and ultimately did not go with that. So, that research jumped overseas and definitely inspired us to think twice about a pure FRP solution for a low posted bridge. Here, the modes of fracture and the brittle failure are shown in a sort of classic finite element model, and principal stresses, as you can see, most importantly, are diagonal at the nib point. That prying action pulls apart the concrete, as you can see, and fails it as it widens and opens. So when that happens, suddenly, though there are internal bars that provide redundancy, overall, that is not how we model typically for the secondary bars, and I want to bring up that major point of limitation. Be it US or software abroad, I'm showing here a finite element model that sort of makes a lot of assumptions for me. It's what bridge engineers use to kind of crank through the dozens and dozens of analyses we have to do in a day and a week, and very quota based. So I'm showing here, like, for instance, the DAPT endpoint is supposed to come up.
The conclusion, because the time is limited.
Oh yeah, sure. Okay. So, so basically the conclusion is we're going to be removing a DAPT end and be bringing kind of a stepped full depth girder into place to increase both its shear strength and its total section. Durability concerns that are addressed here are items such as crack repair and link slab. And I'll post this presentation after. Sorry if that went over. If there's any questions, go ahead.
Thank you very much for your presentation, Jared. Unfortunately, there is no time for questions, so we need to move to the next speaker, but the others can contact you in case.
Okay.
So the next speaker will present nonlinear axisymmetric deformation of shells of complex geometry subjected to mechanochemical corrosion under pressure, and the speaker is Sergei Kabrits. Can you? You're ready?
Yes, I hear.
Yes, go in presentation mode.
I cannot to start presentation while
you should be able to share.
Look, wait a moment.
Yes, we see
Yes.
your screen. We don't see the
I see.
We see your screen. We see the program of the conference on your screen. Okay. Yes, open the presentation.
Can I begin?
Yes, if you open the presentation mode, you can start.
I open the presentation, yes?
Yes, but click on the presentation mode, because now we just see PowerPoint. Next to the minus in the bottom bar of the PowerPoint. Next to the minus, yes, perfect.
Yes.
You can start.
Can I begin?
Yes.
How do you do?
Yes, you can. You can start. Yes.
A shell of rotation is considered. It is a combination of spherical, toroidal, and cylindrical shells with a variable thickness along the meridian. The shell is under the combined action of internal pressure and mechanochemical corrosion. The shell material is elastic. Geometrically nonlinear equation of symmetric deformation of shells of rotation are used to calculate the stress-strain state. It is assumed that an initial moment of time, the shell is under the action of the specified...
Excuse me, we only see your first slide. Maybe you should...
Next slide.
Yeah, you should move manually through the slides. With the arrows.
Yes?
Correct.
It is assumed that at the initial moment of time, the shell is under the action of the specified static loads. Next comes the process determined by models of mechanical corrosion. Due to corrosion, the thickness of the shells decreases, which in turn leads to an increase in stresses. An increase in stress is accompanied by the increase the corrosion rate. The resource of the structure is estimated depending on the geometric parameters. Slide number 2 shows a system of ordinary differential equation. One is the three continuity equations and three equilibrium equations. Formula number 2. In this slide, we can see the relation of elasticity. In as an example, we use the equation of linear equations of elasticity. Model of mechanical corrosion. It is assumed that on the inner and outer surface of the shell, the dependence of corrosion on stresses is expressed by formulas 5 and 6. Here, A, M, B is M, E, B are constants determined experimentally. T is time, sigma is the equivalent stress. H in, Hx measured from the median surface, they are the change in the half thickness of the shell. I emphasize that H in and Hx are the shell thickness that are destroyed as a result of corrosion from the internal and external surface, respectively. The thickness of the shell at each time will be determined by the formula 7. It is assumed that at the initial moment of time, the shell is under the action of specified static loads, for example, internal working pressure. Next comes the corrosion process defined by formula 5, 7. The maximum stresses are calculated, the resource of structure is estimated. The solution of nonlinear boundary value problems in spatial variable is carried out by the method of multiple shooting. To decrease equation 5, 6 in time. To decretize equation 5, 6 in time, the Euler method is used. Example, a hemisphere of radius r conjugate to a cylinder of radius r. The radius is equal. At the initial moment of time, the structure is loaded with internal pressure. The graph of maximum stresses at the initial moment is shown as dot line. The corrosion process begins until at some point in the structure, the thickness decreases to half of the origin one. The distribution of maximum stress is given by a solid line. The stress is relate sigma yield. In this experiment, we get 44 years working. In figure 2, all shell stresses membrane bending are constructed. Figure 3 shows the thickness at the initial time, dashed line, and red line at the final time. Thank you very much.
Thank you for your presentation. I would like to ask the audience if there is some question. Yes?
But, I have a question. Have you tried to compare your models with the experimental results?
Special for this test, we cannot do experiment, but exist many experiments which is good согласование. With my English is not very good. Excuse me.
To compare in the future. Okay. So thank you again.
And now we will move to the next speaker. We present correlation between public formation and shooting in 500 reforms. Please, you can share your screen.
Yeah.
We see your screen. No. Okay, now you can share and start the presentation.
You hear me?
Yes, clearly.
Dear assistants, good evening, everyone. I'm Ariles Chris, doctoral student at the University of Mouloud Mamri Tizi in Algeria. Today, I have the honor to present you my modest work entitled Correlation between Fabric Orientation with Defect, Formation and Shearing in Taft Performance. I present to you the plan of our work. We began by introduction and experimental methods, result and discussion, and conclusion. Introduction. Objective of this work is study the effect of fabric orientation on the creation of defect during forming of taffeta roving. Analysis of the influence of orientation of fabric to orientation 22.5 degrees and 14.5 degrees in the direction of the tool axis. Using a tool with a rectangular shape has an angle of attack of a ridge inclined by an angle of 16 degrees investigation of the effect of some process parameters test under 3 different values of blank holder pressure with 2 different configurations of springs. Method design and fabrication in our laboratory of a specific device to carry out the experimental test. Finding the analysis of formed defect and the sharing between warp and weft showed the influence of the orientation of the taffeta and the applied pressure. Experimental method. Specific test bench designed and produced in our laboratory. The bench composed by 3 main components: bench, die, and blank holders. Components are interchangeable to use any desired part geometry. The bench is mounted in an electric cylinder to be set in motion. The die is open to allow the behavior of the reinforcement to be observed, measured during shaping. Springs are used to generate necessary forces for the blank holders to apply the pressure on the fabric. The test consists of placing the fabric between the open die and bench, then placing a blank holder on the applying uniform pressure to it through springs placed on the blank holder. In figure 1, move the bench to perform fabric after forming defect are measured in the different phase of the peripheral. In the picture, we have the fabric forming device designed and produced in our laboratory. So, to perform forming test, we designed a bench specifically for this study. Figure 1. Figure 2, we have the used bench geometry and its dimension. The bench is a modified rectangular parallelepiped with the face inclined at 16 degrees. The bench is a combination of a cube and tetrahedron. Several geometry that promote the appearance of defect given its detail, radii, right angle, and curvature. To facilitate comparison, the 4 main faces of the tool are marked in figure 2. Roving sensor, roving 500 taffeta fabric has density of 500 grams in meters. For each test, a sample of dimension 300 and 300 millimeters is cued, good composite of markers positioned on the yarn's intersection part of the warps and weft is used to measure the geometric defect and shear after forming. In the protocol, we have 2 orientations of the fabric, 22.5 degrees and 45 degrees with respect to the main axis of the tool are used. 4 test configurations were considered by varying 2 parameters, pressure and springs position. 3 pressure were applied to the blank holder, 447 and 72 and 97 millibar. 2 configuration of the springs, 4 springs in place, 4 springs positioned in the middle of the preform, and 8 springs are around the preform as shown in figure 4. We have in picture A the configuration with 4 springs in place, and in B we have 18 springs. So in result, preform obtained under different test conditions, the size of the defect are biggest in the configuration with 18 springs. We have here the result of different preform. We have in A 14 with the configuration 14 springs plus 20 with orientation 22.500 and 18 springs with 22 and 5 degrees, and 40 springs with configuration 45 springs and 80 springs. And here we have the slippage. Here we show the slippage that we find on triple pounds of our preform, and sliding is found on the face of the preform. And the result with slippage, the slippage appears at the triple pounds effect of the geometry. Slippage is more important in the case of 22 and 5 orientation of the fabric. This difference becomes even greater for medium and high pressure. This confirms the effect of the fabric position on preform quality. For both fabric orientation, slippage defects are lower in the case of 44 springs plus configuration. Location of the springs in the corner for 8 springs increase the defect. The greater the pressure, the greater the intensity of the defect. Sliding appears in the middle of the face of the preform. The sliding is lower for the fabric oriented at 45, especially for medium and high pressure. This confirms the effect of the fabric position on preform quality. The intensity of the sliding seems to vary with the pressure. The tendency is not very clear. The amplitude increases, then decreases. Sliding is mesoscopic defect, so it's sensitive to the variability of local condition. Stress historical. We have here the sliding in the different orientation and different configuration. And the share is greater in the case of the 44 springs plus configuration for the 2 orientation of fabric and for all the pressure applied. Overall, the share is lower. In the case of the 45 orientation of the fabric, the share is weak and does not exceed 12 degrees for all the tests. In conclusion, the relative orientation fabric and bench has a greater effect on preform quality. Mesoscopic defects are more important for orientation of 22.5 degrees. Effect of the springs position. The 4 springs plus configuration of the springs seems to be the optimal. The defect evolves proportionally to the applied pressure. Intensity of the sliding appears to vary with pressure, but remains sensitive to local fabric condition. The share is weak and does not exceed 12 for all the tests. Thank you for attention.
Thank you very much for your presentation. Is there a short question from the audience?
Yeah. What?
So we have a question,
Yeah.
and it's the following. Why didn't you investigate, for example, the 0 or the 90-degree direction of the fabric?
In this work, we showed the behavior of the fabric for complex geometry with an angle 16 degrees configuration. With we use the orientation of 0 degrees to the axis of the tool. The defect is invisible for the importance of the defect. So we have to use other orientation, 22 and 5 degrees and 45 degrees. We vary the pressure applied to the blank holder, which are 47 and 72 and 97 millibars.
Okay, thank you again.
Thank you.
This was the last presentation, and I have I would like to close the conference. It was a great pleasure to meet all of you in Rome and in remote mode. We do hope to meet you again in Porto, Portugal, for the third European Conference on the Structural Integrity of Additively Manufactured Materials that will be held next September. Now the conference is finished, and ciao a tutti. Bye bye.
Thank you.
Bye bye.